Good evening and welcome to The Whispering Scientist. Let the noise of the day fall away now and allow your mind to settle as we turn our attention to the calm, endless dark of space. Tonight, our journey begins not with the planet itself, but with the moment of its creation, a moment of immense power and quiet persistence. This is the story of how Jupiter, the king of planets, was born. Long before Earth ever formed, when our sun was still a young and temperamental star, a cloud of dust and gas circled it like a soft, spinning fog. Within that haze lay the simple ingredients for everything to come: ice, rock, and the lightest atoms the universe could make. But something extraordinary happened in one specific region of that vast protoplanetary disk. Matter began to gather faster, clumping together with such focused gravitational hunger that it soon became the largest and most dominant world in the solar system. Jupiter was the first to arrive. To understand how such a magnificent giant came to be, scientists propose two main tales of formation. The first is called core accretion, the idea that Jupiter began as a solid embryo, a rocky, icy core that patiently grew by attracting every nearby dust grain and pebble. Picture it like a colossal snowball rolling downhill but gliding through the silence of space. Every small piece of debris it met was pulled in by its gathering gravity, and the snowball swelled. Once this solid core reached a critical size, perhaps around 10 times the mass of Earth, its gravitational signature became powerful enough to start capturing the surrounding hydrogen and helium gas. It began to inhale the lightest elements before the newborn sun's powerful radiation could sweep that remaining cosmic nursery gas away. What started as a modest collector of icy fragments slowly turned into a world entirely wrapped in the cosmos's lightest elements. The second theory, known as disk instability, paints a slightly different, more dramatic picture. Instead of slow, steady growth, it imagines that Jupiter was born in a kind of cosmic landslide. The disk of gas and dust itself became so massive in certain cooler regions that gravity caused that material to collapse directly, forming a giant planet in one sweeping, turbulent moment. This quick birth would explain how Jupiter could have formed so quickly, within just a few million years, which is barely a blink in the lifetime of a solar system. It had to be a race against time, a rush to capture the available gas before the young sun's winds could dissipate it entirely. If the planet had waited too long, it might have ended up as a smaller world, perhaps like Neptune. But Jupiter won that cosmic race spectacularly, swelling to hold over twice the mass of all the other planets in our system combined. In truth, the reality of Jupiter's birth may be a gentle blending of both these ideas, a solid seed forming first, followed by a rapid runaway inflow of gas, aided by the turbulent and unstable nature of the early disk around it. The sheer scale of its growth led to a phenomenon called the runaway effect. The more material Jupiter gained, the stronger its gravity became, and the more gas it could attract. This process spiraled out of control, pulling in immense amounts of hydrogen and helium until it crossed a specific threshold. Past that tipping point, adding more mass didn't make the planet much bigger, but simply made it exponentially denser, compressing its gases under unimaginable pressure. The composition of Jupiter's atmosphere offers quiet clues to its beginning. It is made mostly of hydrogen and helium, just like the Sun, but it also contains higher levels of heavier elements like carbon, nitrogen, and sulfur. That slight enrichment suggests that Jupiter's building blocks included icy planetesimals, perhaps comets, and frost-coated rocks that drifted through the cold outer reaches of the early solar system. These icy fragments carried volatile molecules, ammonia, methane, and water, into the growing world, locking away the chemical fingerprints of the solar system's youth. In this way, Jupiter acts as a time capsule, an archive preserving what the universe looked like over 4 and a 500 million years ago. This unique composition and immense mass led to the popular myth that Jupiter is a failed star. It is true that it is made of the same materials, but the truth is more subtle and more beautiful. For a planet to truly ignite fusion and become a star, it would need to be roughly 80 times more massive than Jupiter. Only then would the pressure and temperature at its core be high enough to start the slow burning of hydrogen into helium. Jupiter falls far short of that mark. It doesn't burn, it simply glows faintly from the residual heat left over from its initial formation. In the quiet cold of deep space, that warmth is a soft echo of the moment it was born, when the embrace of gravity filled it with energy. Rather than a failed star, Jupiter is better thought of as the closest thing nature allows to a star without the fire, a giant born not in a blaze of fusion, but in the relentless slow pull of gravity. And from that moment on, its mere presence began to reshape everything around it. Its enormous mass acted as the first sculptor of the solar system, subtly stirring the early disk, flinging some debris outward into the cosmic dark, and defining the stable paths of the smaller worlds that would follow. Dust and ice became order, drawn into the orbit of a swelling king. The king of planets had arrived, and from its earliest beginnings its gravity began to hum through the silence, setting the tempo for the entire celestial neighborhood. Now, let the image of Jupiter's birth settle in your mind, that immense gas world forming in a sudden, powerful rush. We now move from its origin to its influence, tracing how this heavyweight champion of the solar system began to use its vast power. Jupiter is not simply another planet in orbit around the Sun. It is the solar system's quiet choreographer, its gravitational rhythm keeping everything else roughly in line. If the Sun is the conductor of our cosmic orchestra, Jupiter is the booming, steady drum in the back, setting the essential tempo. Its sheer mass, more than twice that of all the other planets combined, bends the paths of wandering comets, carves the very shape of the asteroid belt, and subtly influences the safety and stability of the inner planets. Its gravity reaches far beyond its own orbit, a slow, invisible tug influencing our entire celestial neighborhood. When the giant first formed, its gravitational pull was immense enough to completely rearrange the landscape of the early solar system. Vast swarms of icy rocks and early planetesimals were flung outward, sent drifting to the far edges where they became the raw, cold material of distant regions like the Kuiper Belt. Others were drawn inward, either swallowed by the growing planet or steered toward collisions with the inner worlds, delivering both destruction and perhaps the water that would eventually make up Earth's oceans. Even now, billions of years later, Jupiter's colossal presence still echoes in the motion of countless smaller bodies. Nothing in the solar system moves entirely free of its invisible hand. One of Jupiter's most famous roles is that of the so-called cosmic shield. It's often whispered that without Jupiter, Earth might be bombarded by far more comets and asteroids than it is today, rendering our world uninhabitable. There is truth in that idea, but the reality is a little more complicated than a simple tale of a guardian planet. Jupiter's gravity is powerful, but it is also impartial. It doesn't care where objects end up, only that they move according to the laws of physics. Sometimes it deflects truly dangerous comets and asteroids away from the inner solar system, tossing them harmlessly into distant, icy orbits. Other times, however, that same gravitational pull can act as a slingshot, steering objects inward and putting them on a direct path toward Earth. It's a cosmic paradox. The same planet that has likely saved our world many times over may also have been responsible for causing some of its greatest ancient catastrophes. Jupiter is both shield and slingshot, protector and potential troublemaker. On balance, though, its presence has significantly reduced the overall number of devastating impacts over the solar system's history. Without its immense gravitational vigilance, the quiet stability that allowed life to flourish on Earth might never have been possible. Nowhere is Jupiter's shaping power more elegantly displayed than in the asteroid belt between Mars and itself. You might imagine the belt as a dense, chaotic swarm of rocks endlessly colliding. But in truth, it's more like a vast, sparsely populated desert sprinkled with scattered boulders. Jupiter's gravity is the precise reason for that sparseness. The planet's influence reaches across hundreds of millions of kilometers, creating regions of stability and instability that dictate where asteroids can and cannot survive an extended period of time. Within the belt, there are certain special places where an asteroid's orbital period forms a very simple, exact ratio with Jupiter's. For instance, an asteroid might orbit the Sun exactly 3 times for every 1 orbit of Jupiter, or 5 times for every 2. These are known as orbital resonances. While the math sounds harmless, the result for any object caught there is anything but quiet. Each time an asteroid in one of these precise resonances swings around the Sun, it feels a small, repeated tug from Jupiter, always in the same direction. Over millions of years, those tiny, persistent nudges add up, gently amplifying the asteroid's orbit until it is eventually pushed completely out of the region. The result is a series of empty zones within the asteroid belt known as the Kirkwood gaps. If you could graph the distribution of asteroids by their distance from the Sun, you would see deep, silent troughs where these resonances clear the space like grooves carved into a cosmic record. Jupiter's steady, rhythmic motion writes its signature into the solar system itself, an unseen hand carving order into the chaos of drifting stone. Jupiter's balancing act, sometimes protective and sometimes perilous, has shaped the very conditions that allowed Earth to remain a habitable world. Without it, the asteroid belt might have collected enough mass to form another large planet, which would have entirely destabilized the inner orbits. With Jupiter present, the solar system remains dynamic, yet orderly, a profound blend of chaos and structure that endures through billions of years. It doesn't simply orbit the Sun, it orchestrates the slow, deliberate dance of countless smaller worlds. Its gravity pulls comets into curved arcs and sculpts the belts of debris, a subtle yet continuous work of art. The king does not rule through force alone, but through harmony, the quiet, persistent gravity of its presence. Now let's follow that invisible pull a little closer, past the orbits and the resonant zones, toward the massive groups of traveling stones held captive in the planet's sway. Let's continue our peaceful drift through Jupiter's sphere of influence, moving just beyond the main asteroid belt. While Jupiter's gravity is famous for scattering and clearing space, it is also masterfully skilled at gathering. On either side of its orbit, there exist 2 enormous groups of asteroids known as the Trojan swarms. These are not random clumps of rubble, but vast, stable pockets of material locked into step with Jupiter's motion, forming a kind of perpetual cosmic convoy. Imagine 2 invisible points floating in space. One exactly 60 degrees ahead of Jupiter in its orbit, and one exactly 60 degrees behind it. These are known as Lagrange points, specifically L4 and L5. At these points, the gravitational pull of Jupiter and the Sun combine in such a unique and delicate way that small objects can remain parked indefinitely. They are trapped in a self-correcting gravitational balance, moving along with the planet as it travels around the Sun, almost as if they were banners fluttering in a royal procession. The result is 2 massive flocks of asteroids, one leading and one trailing their immense king. The leading group of Trojans is traditionally named after Greek heroes, while the trailing one is named after Trojans from the mythology of the Trojan War. However, over time, astronomers have mixed the names so freely that both camps now host an amusing jumble of mythological characters. Some of these asteroids are large enough to be worlds in their own right, complete with moons of their own, while others are little more than drifting rubble and small fragments. Together they form a kind of celestial archive, preserving the conditions of the early solar system in orbits that have remained undisturbed for billions of years. protected by the planet's vast, stable pull. These Trojan asteroids are also quiet clues to Jupiter's ancient history, hinting at a past of grand planetary migration. Early in the solar system's history, Jupiter did not necessarily stay exactly where we find it today. Theories, like the Grand Tack model, suggest that the planet may have once moved inward toward the Sun before reversing its course and migrating back out to its current position. During that long, slow wandering, it would have captured material from many different regions, sweeping up icy bodies and rocky fragments alike. The Trojans may be relics of that monumental journey, ancient travelers carried along by Jupiter's massive gravitational tides. By studying their composition, scientists hope to read the diary of the solar system's turbulent youth, understanding where Jupiter went and what it dragged along. Beyond the asteroid belt and the Trojan swarms, Jupiter's gravitational reach continues its slow, steady work into the deepest outer darkness, shaping the paths of comets and dwarf planets alike. Long-period comets that occasionally visit the inner solar system often owe their dramatic journeys to Jupiter's distant, subtle influence. Their orbits are gently nudged into elongated, highly elliptical paths that bring them inward to flash briefly across our skies before being flung back into the profound, quiet cold. Even the current arrangement of the outer planets, Neptune and Uranus, may owe part of its structure to the early gravitational games Jupiter played with its fellow giants. Jupiter is, quite literally, the profound and powerful reason our solar system looks the way it does. The planet's gravitational balancing act, sometimes protective, sometimes perilous, has provided the overall structural stability that allowed Earth to remain a habitable world for long enough to foster life. Without Jupiter, the orbits of the smaller worlds would be far less secure. With the king present, the solar system remains a dynamic yet orderly blend of chaos and structure, enduring through billions of years. Jupiter doesn't merely circle the sun, it quietly orchestrates the slow, deliberate dance of countless worlds, both large and small. If you could somehow step outside our solar system and watch it unfold from afar, you would see Jupiter's invisible influence everywhere. Its gravity pulls comets into wide, curved arcs, sculpts the belts of debris, and holds the massive Trojan swarms like precious ornaments on an invisible thread. Every subtle motion, every shifting orbit is part of the slow, cosmic choreography written by this immense world. And yet, for all its might, Jupiter remains a subtle, gentle artist. It does not announce itself with fire or fusion, but with balance and quiet power. Its gravitational reach is vast, but its touch is measured, sculpting, adjusting, and always guiding the flow of matter. Now let's follow that invisible pull a little closer, past the orbits and the Trojan flocks toward the planet itself, where those unseen forces become visible, painted across a surface of swirling clouds and magnificent color. We drift now toward the king's vast, vibrant face, where the movement of gas creates unparalleled beauty. We drift closer now, the immense gravitational fields giving way to the visible surface of the planet. Seen through a telescope, Jupiter is breathtaking, a slow-motion painting in motion. Ribbons of cream, caramel, ochre, and rust swirl across a vast canvas of clouds. No other planet wears such complex and beautiful colors. From this distance, it appears almost calm, like the soft marbling of coffee and cream, but those serene bands are anything but still. Each vibrant hue tells a story of exotic chemistry, temperature, and motion, written in layers of cloud that descend for hundreds of kilometers. To understand those shifting colors, we first need to imagine Jupiter's atmosphere not as a single blanket, but as a towering, magnificent layer cake of gases and ice. At the very top, high above the bulk of the atmosphere, sunlight filters through a haze made of delicate ammonia ice crystals. This layer forms the brilliant white clouds that drift across the highest, coldest regions, reflecting sunlight and giving Jupiter its luminous, creamy tone. Beneath that, perhaps 80 to 100 kilometers down, conditions grow warmer and far more complex. Here, ammonia gas reacts subtly with hydrogen sulfide to form ammonium hydrosulfide, a compound that condenses into the reddish or brownish clouds. Deeper still, far lower than any visible light can easily penetrate, lie the water clouds, enormous dense structures of frozen droplets and vapor that behave more like terrestrial thunderstorms than wisps of mist. These three main decks, ammonia ice, ammonium hydrosulfide, and water, form the scaffolding of Jupiter's immense, layered atmosphere. Together they paint the planet's face, but the real artistry comes from the molecules that tint those clouds. Scientists call them chromophores, tiny chemical compounds that absorb certain colors of light while powerfully reflecting others. Their exact identities remain partially mysterious, but some are believed to be complex sulfur or phosphorus-bearing molecules. Others could be the chemical products of sunlight breaking down ammonia or other gases in the upper atmosphere. What we know is that these pigments are continually created and destroyed by both chemistry and the planet's weather. As gases rise from the deeper, hotter layers and meet the subtle ultraviolet sunlight from above, they react to form new compounds, gently tinting the upper clouds in soft yellows, golds, and brick reds. The process is slow but constant, Jupiter's own version of aging varnish on a massive masterpiece. The bands we see, the alternating light zones and dark belts, are not painted stripes at all, but vast circulating rivers of air that flow in opposite directions. The pale zones are regions of rising motion, where warmer material from below pushes upward, cooling as it ascends and forming those thick, bright ammonia clouds high in the atmosphere. The darker belts, in contrast, are sinking regions where air descends, warms, and clears away the upper clouds, revealing deeper, darker layers rich in ammonium hydrosulfide and other colored compounds. It is as though the planet is breathing, light rising, dark falling, an endless, slow inhale and exhale of gas and chemistry. These belts and zones are not random formations. They are the visible outward signs of Jupiter's immense internal heat and its extremely rapid rotation, which together drive fierce jet streams that constantly circle the planet. The interplay of these winds and temperatures dictates how deep each band reaches, what chemicals it exposes, and therefore what color it takes on. Where gases rise, they cool and condense into pale clouds. Where they sink, they dry out and darken. Seen from afar, this pattern turns Jupiter into a colossal thermal fingerprint. Each visible band is a unique, stable combination of temperature, altitude, and chemical composition. Sunlight also plays its part. Even though Jupiter receives only about 4% as much sunlight as Earth, that light still shapes the atmosphere. Ultraviolet radiation breaks apart molecules, creating a cascade of chemical reactions that produce the chromophores responsible for the planet's ubiquitous tan and red hues. Over time, this slow bombardment alters the colors we see, shifting them subtly from year to year, sometimes brightening, sometimes fading, as if the planet itself is gently changing moods. For all their grandeur, these colors are constantly changing, a visible sign of invisible forces and a reminder that the king's vast surface is a living artwork, continually repainted by physics. Look long enough at those swirling bands, and they begin to feel almost alive. Cream-colored zones stretching like strands of silk, cinnamon belts rolling and folding over one another. A world of cloud and color, forever stirring, forever remade. Now, as we move from the stillness of observation, we must turn to the sheer motion itself, the ferocious winds that draw these stripes and the immense forces that keep them flowing endlessly around the king of planets. We now glide past the colors and textures of Jupiter, seeking the true source of its organized beauty, the wind. From a great distance, Jupiter's stripes look almost painted on, as if some cosmic artist dragged a brush across the planet's surface, leaving behind perfect, endless ribbons of cream and amber. But those bands are not static decoration. They are ferocious winds, flowing with a precision and intensity unmatched anywhere else in the solar system. The entire planet is wrapped in a silent symphony of jet streams, each one moving in opposite directions to its neighbors, circling the globe at hundreds of kilometers per hour. The key to this striped perfection is Jupiter's extraordinarily rapid rotation. Even though the planet is more than 100 times wider than Earth, it spins once completely in less than 10 hours. This rapid rotation means that points near its equator move at incredible tangential speeds over 40,000 kilometers per hour. Such rapid spinning twists and stretches the atmosphere, breaking large currents into narrow, powerful jets that wrap around the planet from east to west. Each powerful jet stream becomes the precise boundary between the light zones and the dark belts, separating regions of rising and sinking air. The result is a world that looks like it has been carefully layered by nature's own relentless centrifugal hand. These alternating bands of wind, some flowing eastward and some flowing westward, form what scientists call atmospheric jet streams. Earth has a few, but Jupiter has more than a dozen, all far stronger and immensely deeper. The reason lies partly in the planet's immense size and partly in how rotation interacts with convection. On Jupiter, hot gas from the interior rises while cooler gas sinks. But because the planet is spinning so fast, those vertical movements are instantly deflected sideways by a powerful force known as the Coriolis effect. It is the same phenomenon that helps twist cyclones and hurricanes on Earth, but on Jupiter, it shapes the entire global weather system. Rising air veers one way, sinking air another, until the whole atmosphere organizes itself into alternating lanes of motion, a planetary racetrack in permanent flow. The light-colored zones, where air rises, are typically regions of gentle, calmer flow. The darker belts, on the other hand, are where air sinks and warms, creating the most turbulent patches. Between them, fierce shear zones form, thin but powerful boundaries where neighboring jet streams moving in violently opposite directions rub against each other. This friction generates immense turbulence, atmospheric waves, and is often where many of Jupiter's swirling ovals and massive vortices are born, like large eddies forming where two powerful ocean currents meet. For a long time, scientists did not know how deep these jet streams actually went. Were the stripes just a thin, colorful pattern painted on the upper atmosphere, or did they extend far below, rooted in the planet's mysterious, dense interior? The answer arrived with the Juno spacecraft, which began orbiting Jupiter in 2016. By carefully measuring subtle variations in the planet's gravitational field as it flew past, Juno could sense how mass moved beneath the visible clouds. The results were astonishing. Jupiter's jet streams extend roughly 3,000 kilometers below the cloud tops, penetrating into layers where the pressure is so great that hydrogen begins to act more like a liquid metal than a gas. These are not merely winds. They are colossal systems penetrating hundreds of times deeper than Earth's deepest oceans. This deep circulation provides a profound hint about how Jupiter's interior transfers heat. The planet radiates more energy than it receives from the Sun, powered by slow gravitational contraction and residual warmth left over from its formation. That powerful internal warmth bubbles upward, setting the entire atmosphere in motion. As the heat rises, the planet's rapid rotation twists it into bands, which then stabilize into the enduring striped pattern we observe today. It is an elegant dance between energy and spin, gravity pulling inward, heat pushing outward, and rotation shaping the flow into ordered chaos. The result is mesmerizing, a world whose visible surface is pure, continuous motion, structured yet unpredictable, violent yet graceful. Jupiter's stripes are more than weather. They are the planet's silent, powerful heartbeat, pulsing endlessly beneath the faint sunlight of the outer solar system. We can almost hear it, the low, rolling rhythm of hydrogen and heat, the harmony of gas and gravity. And somewhere within that ceaseless flow, one single note swells louder than all the rest. It is the voice of a storm that has raged for centuries, vast and defiant, turning endlessly in Jupiter's southern hemisphere. This is the enduring mystery of the Great Red Spot. From the endless, sweeping flow of the jet streams, we now focus on the singular, monumental feature that dominates Jupiter's face. For centuries, the Great Red Spot has turned slowly in Jupiter's southern hemisphere, a storm so enormous it could once have swallowed 3 Earths whole. It is the most famous, most enduring weather system in the entire solar system, a vast, churning oval that has outlived entire human civilizations. Telescopes in the 1700s first clearly recorded it, but by then it was already ancient, spinning endlessly in the deep, ochre atmosphere of the king of planets. At its core, the Great Red Spot is an anticyclone, a high-pressure system that rotates counterclockwise in Jupiter's southern hemisphere, moving opposite to how hurricanes spin on Earth. Instead of drawing air inward and spiraling down, it pushes outward and upward, creating a towering dome of cold, swirling clouds that sit miles above the surrounding atmosphere. The massive storm is perfectly positioned between 2 of Jupiter's strongest jet streams, one moving eastward above it, and the other moving westward below. These powerful, opposing winds stretch the storm into its familiar, slightly oblong oval shape, like a spinning drop of paint caught between 2 colossal conveyor belts. Despite the chaos around it, the Great Red Spot endures, constantly feeding on the very turbulence that surrounds it. This incredible longevity is one of its great mysteries. Most storms on Earth last days, maybe weeks, before losing energy when they hit land or cool water. But the Great Red Spot has raged for at least 350 years and likely far longer. The secret lies in Jupiter's lack of solid ground. On Earth, hurricanes are cut off from their energy source when they meet a landmass. Jupiter has no such surface to interfere. The storm can spin freely, continuously drawing energy from the planet's internal heat and the endless friction between the surrounding jet streams. Like an eddy in an infinite river, it is perpetually sustained by motion itself. Its rotation is fierce. Winds circle the edge of the storm at astonishing speeds, up to 430 kilometers per hour, though the very center remains surprisingly calm, a wide, high eye of cold cloud tops floating far above the surrounding atmosphere. Beneath those visible clouds, the storm forms a layered column that likely extends for hundreds of kilometers deep, perhaps rooted in regions where compressed hydrogen behaves more like a fluid than a gas. The upper layers, which are visible to our telescopes, are merely the magnificent crown of a much deeper planetary phenomenon. Yet even this ancient tempest is subtly changing. Over the last century, observers have watched it slowly shrink. Its once sprawling diameter is now only about half what it was in the 1800s. From a colossal storm large enough to span 3 Earths, it has gradually tightened its grip, becoming smaller and slightly rounder. The cause isn't fully understood. It could be slowly losing energy to nearby jet streams or simply evolving into a more compact, highly efficient vortex. Whatever the reason, the change is gentle, measured in decades rather than days. The Great Red Spot is not dying. It is adapting and reshaping itself in the slow, persistent rhythm of planetary time. Its color, too, shifts with the years. Some generations have seen it as a deep, striking blood-red oval. Others a pale salmon or a faded peach. Scientists believe this distinct hue comes from chemical compounds, perhaps complex molecules containing sulfur or phosphorus, in the storm's upper atmosphere. These compounds are formed when ultraviolet sunlight breaks down ammonia and other gases, creating reddish pigments that coat the high-altitude clouds. As the chemistry of Jupiter's atmosphere changes, or as the storm lifts or lowers its cloud tops, the color changes too. It is as though the storm itself keeps repainting itself, sometimes bold and fiery, sometimes muted and weary. Through sophisticated spacecraft observations, scientists have confirmed that the Great Red Spot is not a flat disk, but a truly towering structure. The cloud tops within the storm rise more than 8 kilometers higher than the surrounding regions. Inside, air spirals upward, cools and spreads outward, creating a high, bright outer rim that catches the sunlight and contrasts sharply with the darker belts around it. The storm's outer edges are chaotic, constantly shedding and reabsorbing smaller vortices. These smaller storms feed into it like tributaries, joining a vast, ancient river, replenishing its spin. It's a perfect example of vorticity recycling, where the very surrounding turbulence keeps the colossal system alive. Energy doesn't simply dissipate. It is transferred, reabsorbed, and eternally reborn within the swirling, magnificent architecture of the storm. In the grand scale of Jupiter's weather, the Great Red Spot is the eldest, the great survivor, the solar system's most patient weather complaint, muttering for centuries without ever running out of breath. Its survival reminds us that even in a world of violent forces, enduring stability can emerge, not through stillness, but through exquisite balance. The storm persists by interacting perfectly with its chaotic surroundings, drawing its deep strength from the very things that would instantly destroy lesser systems. And in its persistence lies something profound, a living symbol of resilience, an eye of magnificent order in a sea of turbulence. As we move outward from the Great Red Spot, we see that its longevity is not an isolated event, but part of a grander system. Weather on Jupiter is not a passing mood. It is a constant, immense performance. Across its vast, cloud-wrapped surface, storms are perpetually born, grow, collide, and vanish in a magnificent, ceaseless cycle of motion and renewal. Every cloud on Jupiter is part of an atmosphere alive with electric energy and intense convection, a turbulent realm powered primarily by deep internal heat rather than sunlight. One of the most profound and striking discoveries about Jupiter's weather came from its immense lightning. Spacecraft like Voyager, Galileo, and Juno have captured brilliant, branching flashes of light, illuminating cloud tops thousands of kilometers wide. These bolts can be hundreds of times more powerful than any thunderstorm on Earth, crackling deep within the planet's water clouds, far below the visible ammonia haze. Their light can pierce through multiple layers of atmosphere, glowing faintly from within like lanterns submerged beneath a sea of vapor. Each strike is the result of continuous convection, warm air rising, cool air sinking, and water droplets colliding, causing static charges to build until the atmosphere discharges in blinding electric fury. Unlike Earth, where lightning is concentrated near the equator, Jupiter's lightning is concentrated near the poles and deep inside the cloud layers, where water exists as both liquid and ice. These regions serve as the powerful dynamo of the planet's weather, fueling vast convective towers that rise through the atmosphere. Imagine an updraft so powerful that it carries water vapor upward for dozens of kilometers before cooling, condensing, and forming towering thunderheads capped by brilliant ammonia ice. When those droplets freeze, they release heat, driving the convection even harder, a feedback loop of heat and turbulence that keeps Jupiter's immense storms eternally alive. Far above these deep lightning factories, the cloud tops display an entire ecosystem of shorter-lived storms. Some are temporary, bright white spots that drift through the belts, compact, oval-shaped storms known as white ovals. Others are darker, brownish features called barges, often appearing within the planet's turbulent belts. White ovals form in regions of high pressure, similar in structure to the Great Red Spot, but smaller and shorter-lived. These ovals can merge over time, growing stronger, or they can fade away, part of a continuous cycle of formation and decay. Barges, in contrast, are lower pressure systems that appear as holes in the upper cloud decks, offering fleeting glimpses into the deeper, darker atmosphere below. They are the quiet inverses of the brighter ovals, complementing Jupiter's weather with subtle contrasts of shadow and light. Sometimes these smaller storms interact in dramatic ways. Two ovals might approach each other, spinning faster as they draw near, and eventually merge into a single, larger vortex. When that happens, the surviving storm often grows stronger, feeding off the combined energy of its predecessors. These mergers and absorptions are not rare. Jupiter's belts are full of such interactions, creating an ever-shifting mosaic of ovals, streaks, and delicate filaments. Despite the immense violence taking place within its clouds, Jupiter's atmosphere has an underlying, persistent rhythm that keeps the chaos in check. The pale zones are areas of rising air and relative calm, vast and luminous, where little turbulence breaks the surface. In sharp contrast, the darker belts are wild, storm-tossed regions of descending air and intense turbulence. Here, powerful winds shear and twist the atmosphere, spawning vortices and waves that travel across thousands of kilometers. Together, the belts and zones form a planetary pulse, a necessary balance between stillness and storm, between calm breathing and deep convective energy. In some regions, towering plumes erupt like slow-motion fountains, columns of rising air that reach tens of kilometers high, topped by brilliant white domes that shine even in the dim light so far from the sun. These immense upwellings transport water, ammonia, and other chemicals from deep within the atmosphere to the upper levels, helping to constantly mix and refresh Jupiter's weather. What makes Jupiter's weather even more extraordinary is that it is powered mostly from within. Unlike Earth, where sunlight drives the winds, Jupiter consistently radiates more heat than it receives from the sun. This crucial internal heat, a powerful remnant of its formation and slow gravitational contraction, stirs the deep layers of hydrogen and helium, driving convection from the inside out. Every storm, every bolt of lightning, and every swirling oval is a direct manifestation of that deeply buried heat escaping into space. From orbit, spacecraft have captured lightning flashing through the clouds, illuminating the night side of the planet with momentary brilliance. These flashes appear as tiny, powerful sparks on a vast canvas, each one representing an immense instant of raw power inside a world where storms are the norm, not the exception. The more scientists observe, the clearer it becomes that Jupiter's atmosphere behaves like a restless, living system, constantly recycling its energy and material through storms that both destroy and renew. This ceaseless transformation has continued for billions of years, a constant, magnificent performance where the planet's pulse is measured in thunder and wind. Now, beneath the swirling colors and endless storms, deeper still, the air grows denser, hotter, and stranger. Pressure mounts, hydrogen thickens, and the boundaries between gas and liquid begin to blur. The visible storms are only the surface ripples of a much deeper ocean of motion, one that leads into realms where matter itself begins to change. We have looked upon Jupiter's storms, but now we must descend beneath them, where lightning fades and sunlight can no longer penetrate. Here, beneath Jupiter's endless clouds, lies a realm of deepening pressure and profound strangeness. It is a world without a defined surface, without solid ground, where air thickens into liquid and atoms themselves begin to behave in ways unlike anything known on Earth. The deeper one imagines going, the more the very laws of matter seem to bend and contort under the crushing weight of gravity's hand. At first, the descent would take you through layers of increasingly familiar gas, mostly the immense amounts of hydrogen and helium that make up the planet's bulk. But the pressure mounts with alarming quickness on Jupiter. A few hundred kilometers down, the atmosphere grows so incredibly dense that it no longer behaves purely like a gas. Hydrogen molecules are packed shoulder to shoulder, pressing against one another until the space between them nearly disappears. Temperatures begin to rise to thousands of degrees, and the gas transitions into a hot, thick, fluid form, still transparent in parts, but heavy, shimmering, and behaving more like a dense liquid than an atmosphere. Continue falling, and the transformation becomes even more dramatic. At depths where pressures exceed 1,000,000 times that of Earth's sea level, hydrogen changes its character completely. The single electrons that normally orbit hydrogen's protons are forced free, stripped away from their atoms by the crushing weight. They move rapidly through the dense fluid like a metallic sea of charge. Hydrogen, the simplest and lightest of all elements, becomes metallic hydrogen, an electrically conductive liquid that can carry current as easily as copper wire. This extraordinary substance does not exist naturally anywhere on Earth and can only form under the crushing pressure of giant planets or in the cores of stars. This vast ocean of metallic hydrogen is thought to make up the bulk of Jupiter's interior. It flows like molten metal, glimmering invisibly in the profound darkness, and may extend for tens of thousands of kilometers toward the planet's center. As this charged liquid metal moves, it generates immense electric currents that give silent rise to Jupiter's truly colossal magnetic field. The planet, in effect, has a swirling, churning ocean of liquid metal hidden beneath its visible clouds. It is one of the strangest and most powerful substances known to science, a liquid metal born not of heat alone, but of sheer, immense pressure. For decades, scientists had firmly imagined Jupiter possessed a distinct, sharp, solid core, perhaps a dense ball of rock and metal hidden beneath its metallic hydrogen mantle, neatly defined and separated. But more recent data, especially from the sophisticated instruments aboard the Juno spacecraft, suggests something far more complex. Rather than a cleanly defined solid core, Jupiter may have what is known as a diluted core, a vast, fuzzy region where heavy elements are mixed gradually into the surrounding metallic hydrogen, instead of forming a sharp boundary. Gravity measurements show that the planet's mass is spread in a fuzzy gradient, not neatly layered like an onion. It is as if the planet's interior was violently stirred at some point in its history, blending rock, ice, and metal deep into the immense metallic sea. This finding adds new depth to our understanding of Jupiter's formation. It suggests that Jupiter's heart is not a tidy sphere of stone, but more like a slow molten storm of heavy elements, perpetually drifting in a sea of metallic hydrogen. Heat still persistently flows outward from this deep interior, a remnant of Jupiter's dramatic birth. The planet radiates more energy into space than it receives from the sun, glowing faintly in the infrared spectrum. This warmth comes partly from residual heat left over from its original gravitational collapse, and partly from the incredibly slow settling of helium droplets within the planet's interior. As helium separates from hydrogen under the immense pressure, it drizzles downward like slow-motion rain in reverse, releasing gravitational energy as it falls. That steady internal rain of helium helps power Jupiter's deep convective motions and ensures the planet's heat engine continues to run. To describe this deep descent is to speak of overwhelming sound and density rather than shape. Pressure increases like a grand choir, swelling in a vast, silent cathedral made of hydrogen. Soft at first, then immense until every molecule seems to vibrate in unison. There is no floor, no final boundary where one could stop. Even the word inside feels inadequate. On Jupiter, everything blends. Gases flow into liquids, liquids transition into metallic plasma, and somewhere in that colossal continuum lies the planet's elusive, fuzzy heart. All the while, the planet's internal heat and deep motion continue to churn, channeling energy upward in slow, steady waves. Every storm on the surface, every flash of lightning, ultimately draws its immense strength from this silent, metallic ocean below. And it is in this metallic heart, where pressure becomes current and matter becomes conductor, that the planet's greatest invisible force is born. Deep within Jupiter's hidden layers, where hydrogen flows like molten metal, the planet's greatest invisible force is born. Here, in the super-compressed metallic heart of the giant, electricity stirs. The potent combination of highly conductive metallic hydrogen and the planet's extremely rapid rotation turns Jupiter into a colossal dynamo, a natural electrical generator operating on a planetary scale. Every 10 hours, the immense planet spins once, and with each rotation, electric currents swirl through that deep metallic ocean beneath the clouds, giving rise to a magnetic field so vast and powerful it would make Earth's look like a tiny toy compass. Jupiter's magnetic field is the strongest of any planet in the solar system, measuring approximately 20,000 times stronger than Earth's at its surface. But strength alone doesn't capture its true, magnificent scale. The field stretches millions of kilometers into space, forming an enormous encompassing bubble of magnetism known as the magnetosphere. If this structure were visible to the eye, it would appear as an invisible cloak surrounding the planet, one so large that if it could be seen from Earth, it would shine wider than the full moon. It is in every sense the king's invisible cape, majestic, immensely powerful, and unbelievably large. This immense field is wholly powered by the motion deep within Jupiter's interior. The metallic hydrogen, compressed under pressures millions of times greater than those at Earth's surface, acts as a highly efficient liquid metal conductor. As the planet spins, these conducting layers move within the magnetic field they themselves generate, reinforcing and sustaining it. It's the same underlying principle that drives Earth's own magnetic field, but on Jupiter, the scale is beyond human comprehension. The planet's faster spin, its thicker conducting layer, and its sheer enormous volume all conspire to make Jupiter's magnetism one of the most dominant and persistent forces in the entire solar system. However, Jupiter's magnetic field is neither neat nor symmetrical. For many years, scientists imagined it as a simple, tidy bar magnet with a north and south pole neatly aligned near the planet's rotation axis. Then came the Juno spacecraft, carrying instruments designed specifically to map the field in exquisite detail. The results were truly startling. Jupiter's magnetic field is revealed to be lopsided and patchy, with its poles significantly offset and twisted. Near the equator, magnetic loops rise and fall unpredictably, creating regions of intense magnetism interspersed with weaker zones. It's as if the powerful dynamo deep within is not spinning on one perfect axis, but rolling and undulating like molten metal, caught in perpetual, turbulent motion. The North Pole, in particular, revealed a strange feature, a cluster of concentrated magnetic spots rather than one clean field line. This localized region of particularly strong and complex magnetism, sometimes referred to as the Great Blue Spot, mirrors the irregularities of the planet's internal fluid flow. It's a profound reminder that Jupiter's heart is not static. It is alive, shifting, and constantly evolving. The planet's magnetic personality is far more intricate than the simple diagrams once drawn in textbooks. The sheer size of Jupiter's magnetosphere defies all intuition. On the day side, where the solar wind constantly presses against it, the field is compressed to a boundary about 7 million kilometers from the planet's center. But on the night side, it stretches away in a vast magneto-tail, a long tapering stream that extends far beyond the orbit of Saturn. This magneto-tail acts like a massive cosmic highway for charged particles, funneling energy and plasma across millions of kilometers. In a beautiful, subtle sense, Jupiter drags its own magnetic shadow through the solar system. Closer in, the magnetic field traps high-energy particles, forming radiation belts far more intense than anything around Earth. These belts are filled with electrons, protons, and ions, some of which are stripped from the surface of Jupiter's volcanic moon, Io. The particles are caught by Jupiter's magnetic field and accelerated to near-light speeds, creating an incredibly lethal environment for any visiting spacecraft. It is a region so intense that electronics must be shielded behind thick layers of metal. To an astronaut, this would be one of the most hostile places imaginable, a silent, swirling storm of radiation within an invisible ocean of magnetism. This magnetosphere doesn't simply trap particles, it shapes entire regions of space. As Jupiter spins, it drags its magnetic field with it, forcing the trapped charged particles into a rotating disk around the planet, the magnetodisk. Imagine an enormous flattened donut of plasma and magnetic field lines spreading outward in the planet's equatorial plane. This magnetodisk stretches far beyond the planet itself, containing regions of intense electrical current that link the planet's upper atmosphere to its massive magnetic tail. These currents are like the veins of a giant organism, circulating energy across unimaginable distances. For all its immense might, the field has a strange elegance to it. Its invisible lines trace graceful arcs, converging only at the poles where they plunge into the upper atmosphere. There, they ignite the most brilliant and powerful auroras in the entire solar system. Rings of glowing energy that outshine any northern lights seen on Earth. They pulse, twist and shimmer, powered not by the sun, but by the planet's own rapid rotation and the continuous dance of its inner moons. It is as though the king's enormous invisible cape has caught fire at its edges, flickering with light as it sweeps through the profound cosmic dark. Following the invisible threads of the magnetic field, we are drawn now to Jupiter's poles, the place where this immense force becomes visibly transformed into light. At these poles, where magnetic field lines converge and plunge into the atmosphere, the planet glows with a light show unlike anything seen on Earth. These are its auroras, vast, circular ovals of ghostly light encircling each pole, glowing not in the familiar greens and reds of our northern lights, but in profound ultraviolet and infrared brilliance, largely invisible to human eyes. If you could somehow watch them directly, they would appear as shimmering curtains of fire, twisting and flickering in slow motion across a world that could encompass 1,000 Earths. Auroras form when charged particles, electrons and ions, crash into a planet's atmosphere, exciting atoms and molecules that then release light as they return to their calm state. On Earth, those particles come mostly from the sun, carried by the solar wind. But Jupiter is fundamentally different. Its auroras are powered primarily from within by the planet's own immense rotation and its magnetic machinery. Jupiter spins so quickly that its magnetic field whips around faster than the surrounding plasma can keep up, creating a vast generator effect that drives colossal electric currents along the magnetic field lines. When those powerful currents reach the poles, they strike the upper atmosphere and release enormous amounts of energy as light. The result is a permanent, glowing ring of auroral emission around each pole. An enormous auroral oval that never fully fades, even on the day side. This main oval marks the visible boundary between field lines connected to the planet's rapidly rotating magnetosphere and those stretching outward into the solar wind. It is effectively the visible edge of Jupiter's magnetic influence, elegantly drawn in light across the polar sky. Within this glowing perimeter are smaller, continuously moving features, arcs, flares, and subtle footprints, each telling its own quiet story about the planet's profound magnetic connection to its moons. Among these moons, Io plays the most dramatic starring role. This small volcanic world is constantly erupting, spewing sulfur and oxygen into space, feeding Jupiter's magnetosphere with a steady supply of charged particles. These ions are immediately captured by the planet's magnetic field, forming a torus, a massive, donut-shaped ring of plasma that orbits along with Io. The constant interaction between Io's motion and Jupiter's magnetic field generates powerful electric currents, which flow along magnetic field lines and converge near Jupiter's poles. Where those currents meet the atmosphere, they create bright, specific spots within the main auroral oval, the so-called Io footprints. These glowing footprints often appear in triplets, a main spot and faint trailing arcs, a reflection of the way currents and plasma waves ripple through the complex field. It is as if Io is leaving silent, glowing footprints across Jupiter's polar sky with every orbit, a constant reminder of the intense electromagnetic bond between the Moon and its colossal parent. Other moons, Europa, Ganymede, and Callisto, also leave their own magnetic marks, fainter sparks along the Great Ring, revealing how intensely interconnected this entire magnetic system truly is. What makes Jupiter's auroras even more extraordinary is their sheer scale and incredible intensity. The main ovals are thousands of kilometers across, and they radiate energy at levels far beyond any earthly aurora. If human eyes could see ultraviolet light, Jupiter's poles would blaze like cosmic fireflies, visible from millions of kilometers away. Spacecraft instruments detect bursts of radiation so powerful that they could momentarily power entire human civilizations. Some of these bursts, called transient flares, occur when the planet's magnetic field reconnects, snapping and realigning in the turbulent interface between Jupiter's magnetosphere and the solar wind. When that happens, particles are accelerated to extreme speeds, colliding with the atmosphere and lighting up the polar regions with sudden, spectacular flashes of brilliance. Unlike Earth's northern lights, which come and go with solar activity, Jupiter's auroras never truly stop. They are a permanent feature, constantly fed by the planet's rapid rotation and its internal magnetic engine. Even when the solar wind is calm, the auroras continue to burn, sustained by the electrical energy generated as Jupiter's magnetic field drags plasma around faster than gravity allows. In effect, the planet itself is the battery, and its magnetic field is the intricate circuitry through which this immense energy flows. Viewed through the right instruments, the auroras are almost alive. Ultraviolet cameras capture their outlines as glowing rings. Infrared sensors reveal hotspots where the atmosphere warms under the particle bombardment. The visual effect would be breathtaking. From orbit, the poles appear haloed in light, broad ovals shimmering with slow waves and flares. Filaments of brightness twist outward into space, where magnetic field lines carry their energy toward the magneto-tail. Every few minutes, bright spots flicker on and off, the clear, telltale footprints of Io or Europa tracing their invisible, energetic paths. It is humbling to realize that all this grandeur comes from invisible forces, electrons and ions guided by magnetic fields colliding with atoms high above the clouds. Yet, from that unseen constant motion emerges something that feels almost spiritual, light born from magnetism, and a silent, structured order emerging from the deepest chaos. In Jupiter's polar skies, physics truly becomes poetry. The Great Red Spot may be the planet's most famous feature, but the auroras are its soul, an ever-burning crown of light fed by motion, magnetism, and time. They are the glowing edges of an unseen empire stretching far into space, linking Jupiter to its moons and to the solar wind beyond. And far beneath those glowing rings and spirals, the rest of the planet continues its quiet rotation. Even the King's invisible cape has luminous edges, and beyond that light, a fainter wonder waits. As we move beyond the bright, chaotic energy of the polar auroras, we encounter one of Jupiter's most subtle features. Even a king, after all, wears a crown, but this one is so faint and delicate that for centuries no one knew it existed. Unlike Saturn's glorious shimmering rings that blaze even through a small telescope, Jupiter's rings are almost completely invisible, made not of gleaming ice, but of dust so fine it scatters only the very faintest light. If Saturn's rings are a magnificent showpiece, Jupiter's are a well-kept secret. a subtle, understated halo that whispers rather than shines. These fragile rings were first discovered by accident in 1979 when the Voyager 1 spacecraft passed behind Jupiter and caught sunlight glinting off a thin band of particles encircling the planet. What the spacecraft saw was astonishingly faint, a narrow, dusky ribbon just above the cloud top stretching around the equator like smoke caught in orbit. Since then, later missions, such as Galileo and Juno, along with powerful Earth-based telescopes, have revealed the system in greater detail. What they found was not one ring, but several, each with its own quiet tone and texture. The main ring, the inner halo, and the two outer, gossamer rings. The main ring is the brightest, though that's a generous word here. If you were hovering nearby, you might only notice it when sunlight strikes it precisely from behind, scattering forward through the fine dust. It lies just above the cloud tops, extending about 55,000 kilometers from the planet's center. Yet its vertical thickness is only a few dozen kilometers. Within this slender space floats a haze of tiny, microscopic grains, mostly fine fragments of silicate rock. These particles are continually generated, launched and replenished by the activity of small inner moons. Two of those tiny moons, Metis and Adrastea, orbit entirely within the main ring itself. They act as both the sources and the sculptors of the dust. When micrometeoroids, tiny, fast-moving bits of space debris, collide with their surfaces, the impacts kick up clouds of fine particles that gently drift outward, forming the ring. Each collision is like a subtle puff of cosmic smoke, and over time, those puffs create a continuous veil. The ring's faint, fragile structure reflects a balance between creation and erosion. Dust is constantly being lost to Jupiter's gravity, radiation pressure, and magnetic forces, and just as constantly replaced by new material from the Moon's surfaces. Closer to the planet lies the halo, a thicker, more diffuse torus of dust that glows faintly in forward-scattered light. The halo isn't a neat, flat band like the main ring, but a puffy, cloud-like structure extending significantly both above and below the ring plane. Here, Jupiter's immense magnetic field plays a major role, subtly tugging on charged dust grains and causing them to move in looping, tilted paths. Instead of orbiting neatly, they spiral slightly, giving the halo its soft, diffuse, aura-like shape. Farther out, the main ring gives way to the gossamer rings, the most ethereal of all. These are formed by two slightly larger moons, Amalthea and Thebe, which orbit farther from Jupiter. Their faint debris trails stretch inward toward the planet, creating overlapping sheets of dust so incredibly thin that they are nearly transparent. These gossamer rings are so delicate that if you held a handful of the material together, it would be barely visible, even in bright sunlight. Their name fits perfectly, gossamer, meaning something so fine it almost isn't there. Jupiter's rings are truly visible primarily when sunlight shines through them from behind, a technique known as forward scattering. In this precise orientation, light gently bounces through the fine dust and becomes visible to spacecraft cameras. From most other angles, they simply vanish, blending perfectly into the profound blackness of space. It's this elusive nature that kept them hidden for so long. To the naked eye, Jupiter appears as a planet with no adornments. Only when the lighting is just right does its subtle crown appear, faintly gleaming like dust motes suspended in a sunbeam. The dynamics of these rings are surprisingly complex. Tiny dust grains feel not only Jupiter's strong gravity, but also the gentle drag of the planet's magnetic field, solar radiation pressure, and the subtle gravitational pull of nearby moons. Each of these forces nudges the particles, gradually altering their orbits. Some drift inward until they are vaporized in the upper atmosphere. Others are pushed outward, spreading the ring's edges. In this way, Jupiter's rings are constantly in motion, eroding, replenishing, and reshaping themselves on timescales of months or years. It is an understated act of maintenance, like a crown that polishes itself through constant, careful use. Unlike Saturn's rings, which gleam with ice and reflect light like mirrors, Jupiter's dusty rings absorb much of the light that hits them. Their muted color, when seen up close, is a subtle red-brown, matching the silicate composition of their source moons. The lack of icy material is another reason they appear so dim. Close to the sun, volatile ices cannot survive. They sublimate away, leaving only rock and dust behind. Jupiter's warmth ensures that its rings remain made of stone, not frost. Their faintness carries a kind of charm. In a solar system of spectacular rings and massive moons, Jupiter's are the quiet ones, modest, transient, but elegantly formed. They remind us that not all grandeur shouts. Some simply glow softly in the dark. It's as if the king of planets decided he didn't need a golden crown at all. Just a thin, transient band of dust, an accessory that whispers, "I could shine brighter, but I don't need to." They are the most fragile jewelry in the solar system, endlessly remade by dust, light, and the passage of time. As we move outward past Jupiter's subtle, dusty halo, we encounter an entirely new system of worlds. Encircling Jupiter is a kingdom of companions, a miniature solar system in its own right. Dozens of moons orbit the giant, each one distinct, each with a story carved from gravity and time. Together, they form a celestial court that mirrors their parent planet's grandeur, some small and ragged, others immense and stately, and a few so extraordinary that they could easily be planets themselves if they orbited the Sun instead. Astronomers have identified nearly 100 of these moons so far, and more continue to be discovered as telescopic technology improves. They fall roughly into two great families. Closest to Jupiter are the regular satellites, primarily the four magnificent Galilean moons, along with a handful of smaller companions. These moons orbit in near-perfect circles, aligned neatly with the planet's equator, a testament to their formation alongside Jupiter from the original swirling disk of gas and dust. They are the true inhabitants, born and raised in this gravitational realm. Farther out lie the irregular moons, a vastly greater number of objects that represent the planet's captured wanderers. They loop around Jupiter in stretched, highly tilted, and sometimes backward orbits, their paths tracing the aftershocks of ancient, violent gravitational encounters. This outer family is a mixed collection of captured asteroids, cometary remnants, and the shattered fragments of earlier moons torn apart by collisions. The Galilean moons, Io, Europa, Ganymede, and Callisto, are the undisputed crown jewels of Jupiter's court. Their story is fundamental to human history. They were discovered in 1610 by Galileo Galilei, who turned his small, pioneering telescope toward Jupiter and saw, to his astonishment, 4 tiny stars lined up beside it. Night after night he watched them change position, moving in lockstep around the planet. It was the first clear, powerful proof that not everything in the heavens revolved around Earth, and in that simple, profound observation, the known universe suddenly grew much larger and more complex. These 4 worlds are among the most fascinating objects in the solar system, each a self-contained world shaped by the overwhelming gravity of the giant they orbit. The orbits of the irregular moons are much more chaotic. They orbit far beyond the Galileans, often in vast clusters that share similar, highly tilted paths. Some move prograde in the same direction as Jupiter's rotation, while others move retrograde, circling the opposite way like rebellious distant courtiers. Their paths are steeply inclined, some tilted almost sideways to the planet's equator, strongly suggesting they were not born here, but were rather taken in much later in the solar system's history. These stray bodies were drawn in by Jupiter's enormous gravitational field, acting like a vast cosmic net. The capture of these distant moons was not gentle. In the turbulent early days of the solar system, Jupiter's gravity snagged passing bodies that wandered too close. Some were slowed down by subtle friction with residual gas or dust in the planet's extended early atmosphere, losing just enough energy to remain perpetually trapped. Others arrived as parts of binary systems, pairs of small bodies orbiting each other, and when Jupiter's gravity tore the pair apart, one escaped while the other was forcibly captured. Many of these irregular moons now form distinct families, likely the debris of larger bodies shattered by massive ancient impacts. Astronomers can trace their shared origins by comparing their orbits and colors, revealing clusters that tell quiet tales of destruction and capture. Closer in, the story is far more orderly, but no less dramatic. The regular moons follow paths intricately carved by orbital resonance, delicate gravitational rhythms that tie their orbits together. Io, Europa, and Ganymede, for example, are locked in a perfect gravitational dance, a magnificent expression of balance that will be explored later. This gravitational synchrony keeps their orbits slightly stretched, generating powerful internal tides that flex and perpetually heat their interiors. It's a quiet but relentless process, gravity kneading worlds like dough, creating immense energy simply from motion. This tidal heating explains the immense character of Jupiter's major moons. Io, the innermost, is a world of fire, its surface constantly erupting with hundreds of active volcanoes. Next comes Europa, where that same tidal energy melts internal ice, creating a hidden global ocean beneath its frozen crust. Ganymede, the largest moon in the solar system, is so immense it generates its own magnetic field. And finally, there is Callisto, heavily cratered and ancient, far enough out that tidal forces are weak, and its surface has remained largely unchanged for billions of years. Together, these four worlds form a beautiful gradient from fire to water to silence, each one uniquely sculpted by its precise distance from the giant. Even the smaller inner moons play crucial, quieter roles. Metis, Adrastea, Amalthea, and Thebe orbit close to Jupiter's cloud tops, continually contributing dust to the planet's faint ring system. They are irregularly shaped and heavily battered, remnants of the early system that somehow avoided destruction. Despite their size, they are vital attendants, silently keeping the king's subtle crown intact. Jupiter's gravitational influence extends so far that its family of moons and captured debris could almost be considered a complete, miniature version of the solar system itself. The planet's gravity dominates a vast region called its Hill sphere, an invisible boundary where Jupiter's powerful pull simply overpowers the Sun's. Within this space, it has gathered companions of every kind, volcanic, icy, rocky, and dusty. Each one moves to a rhythm set by the planet's colossal mass and constant motion. The King's Court is one of endless complex motion, a grand, slow waltz of dozens of bodies held together by invisible, ancient threads. And among them all one stands out as the most restless, a volcanic herald whose surface is constantly remade by eruptions and internal tides. From the majestic, quiet order of Jupiter's celestial court, we turn our gaze inward to the most violent and active world within it. Io, this moon is a contradiction in motion, a world that truly never sleeps. It is the most volcanic body in the entire solar system, a restless sphere whose surface is constantly erupting, reshaping, and renewing itself at an astonishing pace. At any given moment, somewhere on Io, a volcano is fiercely blowing molten sulfur and silicate rock into space, painting the landscape in vivid shades of yellow, orange, and deep red. To look upon it is to see a world forever caught in a catastrophic internal struggle, a planet-sized cauldron powered not by sunlight or internal radioactive decay, but by the relentless, invisible tug of gravity. The extraordinary source of Io's energy lies in its tight orbit around Jupiter, where gravity acts as a kind of slow, powerful drumbeat of destruction and renewal. Io's path is not perfectly circular. Because it is locked in a powerful gravitational resonance with its siblings, Europa and Ganymede, Io moves in a slightly stretched ellipse, continuously drawing closer to and then farther from Jupiter during each orbit. Every time it approaches, Jupiter's immense gravity pulls harder, flexing the Moon's solid interior. Then, as Io moves away, that pull gently relaxes. The entire Moon stretches and compresses, or breathes, with each cycle, creating enormous friction deep inside its mantle. This continuous tidal flexing releases an immense amount of heat, as much energy as 1,000,000 terrestrial volcanoes combined, melting rock and driving the constant, vigorous eruptions that define its surface. Imagine the entire crust of a world rising and falling by dozens of meters over and over again for billions of years. That is Io's existence. Its surface, which should have cooled and hardened long ago like our own Moon, instead behaves like a thin, fragile crust floating over a simmering global ocean of molten magma. Where the pressure becomes too great, it cracks, and immense fountains of molten sulfur and silicate rock burst forth, some shooting hundreds of kilometers high. These eruptions can last for months, even years, covering vast regions with new layers of lava and frozen sulfur frost. When spacecraft like Voyager, Galileo, and Juno have glimpsed Io, they've seen a surface that seems truly alive, glowing with active plumes, glowing lava lakes, and constantly shifting colors. Unlike Earth's volcanoes, which cluster around tectonic boundaries, Io's volcanoes are scattered everywhere across its surface. The entire Moon is geologically active from pole to pole. Its mountains rise higher than Mount Everest, formed not from plate collisions, but from the immense buckling and uplift of the crust under overwhelming internal pressure. Vast plains of frozen sulfur stretch between the peaks, spectacularly mottled by bright yellows and deep reds from the unique chemical reactions on the surface. The vibrant colors come directly from sulfur in different forms: brilliant yellows from freshly erupted deposits, oranges and browns from older, more weathered material, and darker reds where the intense heat has baked the minerals into new, complex compounds. Seen from orbit, Io looks like an artist's palette that has been left too long in the sun. Brilliant, but utterly chaotic. The volcanic plumes that rise from its surface are colossal, dwarfing anything seen on Earth. Some soar over 300 kilometers into space, so large that they can be clearly seen silhouetted against the blackness behind the Moon. They are primarily made of sulfur dioxide gas and fine dust, hurled upward by explosive eruptions, then falling back like a thin, toxic snow. These plumes help form a faint, patchy atmosphere that clings to the Moon for only short periods before freezing or escaping into space. Each eruption briefly replenishes it, keeping Io surrounded by a thin, ever-changing haze. But Io's influence doesn't end with its own sky. The gases escaping from its volcanoes are instantly caught by Jupiter's incredibly powerful magnetic field, stripped into ions of sulfur and oxygen, and swept into orbit around the planet. There, they form a vast, glowing ring of charged particles known as the Ioplasma torus. This invisible, energetic river of ionized gas completely encircles Jupiter, connecting the Moon directly to the planet's magnetic system. As Io moves through it, immense electric currents flow along magnetic field lines between the two worlds, a gigantic natural circuit stretching nearly 500,000 kilometers. The energy carried by these currents helps to power Jupiter's auroras, linking the Moon's volcanic fury directly to the spectacular shimmering lights at the planet's poles. For Io, this relationship is both beautiful and brutal. The magnetic field bombards the Moon with radiation, constantly ionizing its atmosphere and surface. It is one of the harshest, most volatile environments anywhere in the solar system. Yet through this constant dynamic exchange, Io and Jupiter remain eternally intertwined, a fiery moon feeding an invisible magnetic sea. The landscape of Io is a spectacular contradiction. There are almost no impact craters visible because the surface is constantly renewed. Old scars are quickly erased by new lava flows and deep blankets of sulfur dust. Every few million years, the Moon's entire crust may be recycled, completely resurfaced by volcanic activity. It is, in essence, a living world, but one that thrives on ceaseless internal destruction. Io teaches us that planets and moons are not static places. They live, they change, and they evolve. Its fire is a powerful reminder of the energy still hidden within the heart of worlds, waiting only for the right kind of gravitational motion to wake it. And just beyond it, orbiting in the same powerful rhythm, lies another moon born from that same gravitational tension, a frozen world hiding a vast, dark ocean beneath its icy shell. From Io's world of fire and sulfur, we now travel to its immediate neighbor, Europa, a frozen world that exists in profound contrast. Europa is one of the most beautiful enigmas in the solar system, a world wrapped completely in ice, silent on the outside, but whispering secrets from below. Its surface gleams pale and smooth, an immense frozen mirror reflecting the faint sunlight that reaches Jupiter's domain. But beneath that gleaming shell, scientists are now convinced there exists an entire ocean, vast, dark, and warm enough to remain liquid and flow. If this is true, Europa could hold more water than all of Earth's oceans combined. It is the quietest world in Jupiter's immediate court, and yet, beneath the silence, something truly profound stirs. At first glance, Europa looks pristine and calm. There are remarkably few impact craters, which is a powerful clue that the surface must be geologically young, constantly renewed and smoothed over time. Instead of high mountains or deep canyons, the Moon is etched with long, dark streaks that crisscross its icy crust, the famous lineae that stretch for thousands of kilometers. These marks look like cracks in old paint, but they are in fact scars of constant motion. As Europa's interior continuously flexes under Jupiter's immense gravitational pull, the rigid ice shell stretches and fractures. When the cracks open, material from below rises to fill them, leaving behind dark, reddish-brown ribbons that precisely trace the paths of stress across the Moon's surface. Those visible streaks and the chaotic, broken regions known as chaos terrains are our primary clues that Europa's shell is not solid all the way down. The surface appears to float atop something that can flow, almost certainly a global ocean lying beneath 10 to 30 kilometers of protective ice. In some regions, the ice looks shattered and rearranged, as if enormous slabs have drifted, rotated, and refrozen, much like pack ice on Earth's polar seas. These patterns strongly suggest continuous motion beneath the crust, and motion means internal warmth. That warmth comes from the exact same powerful tidal dance that fuels Io's volcanoes, though Europa's response to it is far gentler. Locked in orbital resonance with Io and Ganymede, Europa is constantly stretched and squeezed by Jupiter's immense gravity. This rhythmic flexing generates continuous internal heat within the Moon, not enough to melt the surface ice, but enough to prevent the vast subsurface ocean from freezing solid. The process is subtle, but relentless. Energy is drawn from the Moon's orbit and converted into persistent, internal warmth, a gravitational heartbeat that has pulsed for billions of years. Evidence for this hidden ocean comes from several powerful lines of observation. When the Galileo spacecraft flew past Europa in the 1990s, it detected slight fluctuations in the Moon's local magnetic field. These variations hinted strongly at a layer of electrically conductive material beneath the surface, which is most likely a global, salty ocean. Later, tantalizing observations from the Hubble Space Telescope revealed faint plumes of water vapor rising from the Moon's southern regions, shooting hundreds of kilometers into space before gently falling back to the surface. These plumes, if confirmed as originating from the subsurface ocean, would be the most direct evidence yet of water escaping from below, geysers on an alien sea, revealing the contents of the hidden deep. Europa's surface itself tells a story written in ice and salt. Spectroscopic studies suggest that the dark material along its fractures and chaos regions contains salts similar to those found in Earth's deep oceans, such as magnesium sulfate and sodium chloride. This hints at crucial chemical interactions between the dark, rocky seafloor and the water, a massive exchange occurring far from sunlight. It is entirely possible that Europa's ocean lies atop a rocky bottom where water and rock meet in perpetual darkness. If so, chemical reactions could be occurring there, much like those around hydrothermal vents on Earth's ocean floors.
On our planet, those vents teem with life.
But talk of life on Europa must be made carefully. The ingredients for life are tantalizingly present: water, the necessary chemistry, and energy. Yet that doesn't guarantee biology. The ocean may be warm and salty, yet entirely lifeless, a quiet abyss of chemistry without consciousness. Still, the possibility remains that even the simplest microbial existence could be clinging to rocks beneath kilometers of ice, and that possibility alone would fundamentally change how we view life in the cosmos. It would suggest that life is not a rare accident, but a natural, persistent outcome of planetary evolution, something that arises wherever water and energy find a sustained balance. The immense mystery is deepened by how little we can truly see. Europa keeps its ocean hidden, speaking only through subtle clues, magnetic ripples, surface fractures, spectral fingerprints, and the occasional whisper of vapor above its poles. It has been called the shyest ocean in the solar system, endlessly fascinating because it is always covered, never directly seen. The idea of a world with a buried ocean has captivated scientists and dreamers alike. Future missions are now being prepared to explore it more closely, such as NASA's Europa Clipper spacecraft, which will make dozens of flybys to map the ice, measure its chemistry, and specifically search for plume activity. Europa invites a profound, quiet wonder. It doesn't dazzle with color or noise. It doesn't roar like Io or shine like Jupiter's storms.
Its beauty lies in suggestion, the smooth glint of sunlight on its ice, the delicate tracery of its cracks, and the immense promise of an ocean moving unseen below.
It is a powerful reminder that not all profound possibilities need to announce themselves loudly. Sometimes the greatest secrets lie hidden beneath layers of silence. Now, just beyond it, waits another moon, larger, magnetized, and carrying its own distinct story of ancient oceans and frozen time. From the potential liquid warmth of Europa, we drift outward to its next majestic neighbor, Ganymede. This moon is truly the monarch among moons, the largest in the solar system, even surpassing the size of the planet Mercury. Yet despite its colossal size, it carries itself with a quiet dignity, a calm, vast world orbiting a turbulent giant. Ganymede is a place of paradoxes, immense and ancient, scarred yet profoundly serene. Deep within its frozen heart, it holds a secret no other moon can claim, a magnetic field of its own. Discovered by Galileo in 1610 along with its siblings, Ganymede immediately stood apart. It was not just large, but luminous, reflecting sunlight off an icy crust that is dramatically crisscrossed with pale, intricate grooves and large, darker patches. When sophisticated spacecraft later revealed its true nature, scientists realized it was not merely a frozen ball of rock, but a fully differentiated world, a planet in miniature, complete with a distinct core, mantle, and crust.
Layered much like Earth itself.
Beneath its rugged surface lies a potentially deep, salty ocean trapped between immense sheets of ice. And at its very center, a core of molten iron still slowly flows, turning and generating a magnetic field that hums faintly through space. That unique magnetic field is Ganymede's defining signature feature. Among all the moons in the solar system, it is entirely unique.
Even Earth's moon and Mercury's weak magnetism pale in comparison to Ganymede's strength.
The field creates tiny, energetic auroras at Ganymede's poles, shimmering in ultraviolet light, where charged particles collide with the thin traces of its tenuous oxygen atmosphere. More intriguingly, this field interacts directly with Jupiter's enormous magnetosphere, forming a miniature magnetic bubble fully enclosed within the larger one. It is a magnetic world orbiting within a magnetic kingdom. The effect is a dynamic dance of currents and fields, a constant, energetic interplay between the Moon and its parent planet. The very existence of this field tells us something profound about Ganymede's interior. To sustain it over billions of years, the Moon must possess a molten metallic core, most likely iron or iron sulfide, which remains in turbulent motion. That motion drives an internal dynamo much like Earth's, powered by slow cooling and the crystallization of heavier elements toward the center. It is as if deep within this frozen world there lies a hidden furnace, an iron heart that still beats faintly beneath the ice and rock. Above that core lies a thick mantle of silicate rock, and above that layers of ice and potentially liquid water. Models suggest that Ganymede's vast ocean, if it exists, might be sandwiched between two sheets of ice, forming a unique layered ocean structure: ice, then liquid water, then another layer of high-pressure ice below that. In total, this immense ocean could contain more water than all of Earth's combined, though it remains permanently sealed beneath hundreds of kilometers of frozen crust. Even so, subtle signs of motion persist. Magnetic measurements indicate that the ocean is likely salty and electrically conductive, its internal movement subtly influencing the Moon's external magnetic field. In this way, Ganymede's magnetism not only hints at metal below, but also conductive water above, a dual nature of fire and ice intimately intertwined. The surface of Ganymede tells the remarkable story of a world that once profoundly stirred with tectonic energy. Its most striking features are its grooved terrains, long parallel ridges stretching for hundreds of kilometers across the bright, icy plains. These grooves are believed to be the result of past tectonic stress, formed when the crust was pulled violently apart and icy material from below welled up to fill the vast gaps. They crisscross the surface in intricate patterns, overlapping older impact scars and dark regions. Some areas are smooth and bright, others fractured and shadowed, giving the Moon a textured look unlike any other body in the solar system. Between these magnificent grooved expanses lie ancient dark terrains, remnants of Ganymede's original crust. They are heavily cratered, scarred by impacts dating back billions of years, their features slightly softened over time by slow, subtle flows of ice. These darker regions contrast sharply with the bright streaked plains, telling a geological story of simultaneous renewal and preservation, of a Moon that once strongly flexed and shifted before slowly cooling into relative stillness. It is a vast, frozen record of ancient activity. Despite its violent history, Ganymede today is a world of comparative calm. It lacks Io's volcanic fury and Europa's active fracturing, standing instead as a monument to stability. Its gravity is strong enough to shape a thin, tenuous atmosphere, made mostly of oxygen molecules broken from the surface ice by sunlight. This subtle atmosphere adds to the sense that Ganymede is a complete, self-contained world. It is not merely a satellite, it is a planet that happens to orbit another. If one could stand on Ganymede, the sky would be magnificent. Jupiter would hang enormous above the horizon, its clouds faintly colored by distance, surrounded by the other moons moving along their precise paths. The surface beneath your feet would crunch softly with frost, and the silence would be so profound that you could almost perceive the faint hum of magnetism, the slow turning of that iron heart deep below. Ganymede's serene appearance belies its profound complexity. It bridges worlds between rock and ice, between internal motion and external stillness, between the inner warmth of metal and the outer chill of space. It is a moon that has found an ultimate equilibrium, carrying both the memory of its fiery beginnings and the quiet patience of its frozen present. In its quiet endurance, it embodies a kind of cosmic grace, a silent reminder that strength doesn't always roar. Sometimes it simply resonates softly, like the deep tone of an unseen bell. As we drift outward from Ganymede's magnificent magnetized orbit, the light begins to subtly fade. The final great moon, Callisto, lies farthest from Jupiter's warmth and strongest tidal forces, dimmer, darker, colder, yet still quietly stirring in its own ancient way. Callisto is the elder of Jupiter's great moons, a world that is ancient, quiet, and profoundly unhurried. While its three siblings dance to the relentless rhythms of tides and magnetism, Callisto drifts serenely on the outskirts of the system, far enough from Jupiter to largely escape the gravitational tug-of-war that constantly stirs the others. Its surface, dark and heavily cratered, has remained almost entirely unchanged for billions of years. It is a world that truly remembers everything. Every ancient impact, every scar, every story from the solar system's turbulent youth is still visibly written upon its face. If the moons of Jupiter were a royal court, Callisto would be the archivist, patient, reserved, and utterly unwilling to discard a single volume of its past. Seen through a telescope, Callisto appears mottled and subdued, its shades of grey and brown blending into a calm, dusky sphere. But close up, spacecraft have revealed a surface unlike any other, a dense quilt of craters upon craters, packed so tightly that even the craters themselves have secondary impact scars. There is virtually no evidence of recent volcanic activity, no immense ridges or deep grooves like those etched into Ganymede, and no flowing ice plains like Europa's. It is as if the moon froze early in its history, perhaps within the first billion years, and has slept ever since, quietly collecting the signatures of cosmic time. This powerful lack of recent geological activity makes Callisto a kind of planetary fossil. Its surface perfectly preserves a record of impacts stretching back to the earliest days of the solar system, when asteroids and comets still roamed freely, colliding and merging to form the planets and moons we know today. Each crater tells a part of that dramatic story, from vast, multi-ring basins to the smallest pockmarks left by ancient debris. The largest impact feature, the Valhalla Basin, spans nearly 4,000 kilometers, an enormous concentric pattern of subtle ridges that ripples outward from a central impact point. It is not just a crater. It is a frozen echo of a violence so immense it shook the entire moon and left a permanent scar visible across half its face. Unlike its more dynamic siblings, Callisto shows little compelling evidence of strong internal differentiation. When the moon formed, it seems to have never fully melted inside, meaning that rock and ice remain generally mixed throughout rather than separating into neat layers of core, mantle, and crust. This gives it a lower density and a simpler, less energetic structure. In many ways, it is the most primitive of the 4 Galilean moons, a vast, preserved snapshot of what the early building blocks of planets might have looked like before internal heat and gravity began to reshape them. Yet, even this quiet world may hide a few surprises beneath its profound stillness. Magnetic readings taken by the Galileo spacecraft hinted that Callisto might possess a subsurface ocean, much like Europa and Ganymede. The evidence is not as definitive, but it is deeply intriguing. Subtle changes in the magnetic field suggest a weakly conductive layer beneath the battered surface, possibly a salty, liquid water ocean trapped under hundreds of kilometers of cold ice. If it exists, it would be a dark, cold sea, far from the warmth of the sun or the active tidal heating of Jupiter, sustained only by the slow, faint decay of radioactive elements within its core. This possibility adds a layer of depth to Callisto's serenity. Beneath its ancient, battered crust, there may be movement, after all, slow convection, faint warmth, and perhaps even the basic chemistry of water and rock mingling in silence. But on the surface, nothing betrays this internal possibility. The moon presents itself as timeless and still, a monument to endurance rather than dramatic activity. It has no magnetic field, no geological renewal, and only the thinnest wisp of an atmosphere. It simply circles Jupiter, observing unchanged. Callisto's profound quiet is its greatest gift to science. In that stillness lies history, the oldest, most complete record of the early solar system anywhere beyond the asteroid belt. Scientists often describe it as a time capsule, a body that preserves conditions from the epoch of planetary formation. By studying its craters, its surface composition, and its unique chemistry, we gain glimpses of what the solar system looked like 4 billion years ago, when impacts were frequent and young worlds were just beginning to take their shape. The contrast with its siblings is striking.
Io burns. Europa hides an ocean beneath restless ice.
Ganymede hums with its own magnetism. Callisto does none of these things. It remains at peace, orbiting far enough from Jupiter that tidal forces are weak. Its interior spared the constant flexing and friction that have kept the others geologically alive. That distance has made it stable, a moon untouched by the dramatic storms of its family. Where the others evolve, Callisto endures. Its landscape is full of quiet poetry. It is a survivor, content to remember. Its refusal to change is what makes it so profoundly valuable. In an environment where so many worlds are restless, Callisto's stillness is its strength, a stable archive, quietly holding on to the memory of the solar system's violent youth. And as we drift back from Callisto, from this archivist who guards the memories of creation, we are reminded that all of these 4 worlds, despite their differences, are connected by an invisible, precise and ancient relationship. They are bound together by the very force that set their orbits and whose pull maintains the rhythm of their tides. It's time to look closely at that rhythm now. The moons of Jupiter do not wander aimlessly. They move in rhythm, a vast, invisible symphony conducted by gravity itself. Each orbit, each subtle tug, each slight acceleration is part of an intricate choreography that has lasted for billions of years. Among all these celestial dancers, 3 stand out for their breathtaking, magnificent precision: Io, Europa, and Ganymede. Together they form what astronomers call the Laplace resonance, a gravitational pattern so elegant and precise that it feels less like an astronomical accident and far more like ancient music written directly into the fabric of space-time. In this magnificent cosmic arrangement, every time the outermost of the trio, Ganymede, completes a single full orbit around Jupiter, Europa goes around twice, and the innermost, Io, completes exactly 4 orbits. Their orbital periods are locked in a perfect 1-2-4 ratio, a gravitational harmony that keeps the trio eternally and intimately connected across the blackness of space. Though separated by millions of kilometers, they pull on one another with an exquisite, delicate timing that allows their combined gravity to always exert a maximum influence at precise, predictable moments. These regular, persistent gravitational nudges prevent their orbits from ever becoming perfectly circular. Instead, they remain slightly stretched or elliptical, and that subtle distortion, that slight, continuous breathing motion, makes all the difference in their world. The stability of the resonance is not quiet. It is loud with power. The moons constantly exchange energy and angular momentum, keeping one another's orbits perfectly aligned over vast stretches of time. Without this arrangement, Io's orbit might slowly decay, Europa might drift outward, and Ganymede's rotation might slow, but the resonance locks them into a repeating cycle where every tug and pull is perfectly countered by another. It is a profound gravitational handshake that keeps the entire system synchronized. The constant gravitational squeezing and releasing, known as tidal flexing as the moons move closer to and farther from Jupiter, generates
enormous friction deep inside their interiors.
This process converts their smooth orbital energy directly into raw thermal energy. For Io, the innermost and most frequently flexed moon, this intense tidal flexing causes its mantle to melt, its core to heat, and its surface to constantly erupt in hundreds of volcanoes. It is a world of eternal fire, powered not by the sun, but by the relentless, precise mathematics of its motion. The same rhythmic forces act on Europa, but because it is farther out, its response is far gentler. The heat generated there is not enough to fuel explosive volcanoes, but it is precisely enough to keep a vast subsurface ocean liquid beneath its kilometers thick, icy shell. A dark, deep sea warmed entirely by invisible persistent tides. Even Ganymede, the farthest of the trio, feels this rhythm. The heat generated in its deeper layers may help maintain the molten metallic core that gives rise to its unique magnetic field. In this stunning way, a single, shared gravitational pattern distributes life-changing energy across three entirely diverse worlds, shaping volcanoes on one moon, oceans on another, and magnetism in a third. It is a true celestial energy network powered entirely by motion. The beauty of the Laplace resonance lies profoundly in its balance. The interactions are governed by the same physical laws that make pendulums swing in rhythm or musical strings vibrate in harmony. Gravity, though invisible, behaves here like a colossal spring, one that can store and release immense energy across unimaginable distances. Each moon's orbit adjusts ever so slightly in response to the others, the way a note bends when played alongside a resonant chord. Over time, these precise adjustments add up to a deep, enduring stability, a self-correcting pattern that perpetually resists chaos. This kind of resonance isn't rare in the universe, but few examples are as dramatically powerful or as enduring as Jupiter's. This energy exchange is a quiet reminder that even in the depths of space, motion is never truly free. Every orbit carries a cost, every tide a profound consequence. The immense heat that glows from Io's volcanoes and warms Europa's ocean ultimately traces back to the slow, invisible loss of orbital energy, the same way a clock spring unwinds as time moves forward. Gravity here is not only the sculptor of worlds, but their metronome, ticking endlessly, ensuring that the rhythm continues. To picture this resonance, imagine a grand, ancient clockwork suspended in space, with gears made of moons and springs made of space-time. Each gear turns at its own pace, yet every rotation affects the next, transmitting motion through gravitational tension. This mechanism doesn't grind or creak. It flows, its motion so smooth that it appears effortless. And yet, within that smoothness lies immense, unimaginable power, enough to melt stone, sustain oceans, and shape the magnetic fields of worlds. The Laplace resonance is, quite literally, the soundless heartbeat of Jupiter's inner moon system. It is astonishing to realize how enduring this balance has been. Simulations suggest that this perfect resonance may have persisted for billions of years, surviving planetary migrations, massive impacts, and internal structural changes. It is a profound structure that resists both collapse and chaos, perpetually recalibrating itself. Even slight perturbations, a passing asteroid or an evolving orbit, are eventually absorbed into the pattern. Gravity doesn't simply bind, it organizes, and in organizing, it creates. Without this resonance, Io would cool and quiet, Europa's ocean might freeze solid, and Ganymede's magnetic heart would surely fall silent. The very diversity that makes Jupiter's moons so fascinating exists because of this shared, internal rhythm. Beyond the physical, there is a quiet, deep poetry to this connection. The same fundamental force that pulls the tides on Earth also choreographs this magnificent ballet around Jupiter. It reminds us that the universe is not merely a random collection of objects, but a vast web of precise relationships, each thread tugging gently on the next. This is the quiet genius of Jupiter's realm. Chaos tamed by resonance, heat born of gravity's rhythm, and time measured in tides. A system that endures not because it avoids tension, but because it fully embraces it, perpetually turning stress into motion and motion into profound internal warmth. And now, beyond those carefully balanced moons, the planet itself continues to hum with energy, storms swirling above, particles racing within its magnetic field. The clockwork of gravity now gives way to the turbulence and light of the vast central engine that makes Jupiter itself alive. As we step back from the careful, precise ballet of Jupiter's moons, we turn to the vast engine that powers their entire system. Jupiter glows with an internal warmth that does not come from the Sun. Though it lies more than 700 million kilometers from our star, the giant planet shines faintly in infrared light, consistently radiating nearly twice as much energy as it receives. In a solar system where most worlds rely entirely on sunlight for their warmth, Jupiter makes its own. It is a world that has simply never quite cooled off, still gently shedding the immense energy it was born with.
Billions of years after its initial formation. That fundamental,
Enduring internal heat defines almost everything about Jupiter's magnificent atmosphere and its perpetual climate. Deep within, the planet's interior remains intensely hot from its original gravitational compression, the incredibly slow squeeze of hydrogen and helium under the overwhelming weight of the world itself. As the planet contracts ever so slightly over vast eons of time, it converts enormous amounts of gravitational potential energy into thermal energy, perpetually warming the gases from within. This subtle, long-term settling is what scientists refer to as Kelvin-Helmholtz contraction. But in simpler, more peaceful terms, Jupiter is still slowly settling into itself, patiently radiating the residual warmth of an unfinished, ancient birth. This slow, internal leak of heat steadily rises upward, escaping through layers of dense gas and thick cloud. It is this escaping heat that powerfully fuels convection, the same basic process that drives boiling water on a stove, but operating on a scale so vast that entire continents could fit within a single, rising convective cell. Warm gas from the planet's depths rises, cools, and then sinks again in enormous, continuous cycles, churning the atmosphere and perpetually feeding the planet's endless weather. These powerful vertical motions carry energy through the colossal column of gas, forming the stable belts and zones that elegantly stripe Jupiter's surface, the ovals and vortices that dance rhythmically between them, and the towering storms that flash with electric lightning deep in the clouds. Because Jupiter's internal heat is so immensely strong, it dominates over sunlight in driving the planet's weather. Even though the planet receives only 4% of the sunlight that reaches Earth, its atmosphere remains eternally restless and highly dynamic. The Sun's contribution is little more than decoration. It paints subtle differences in temperature between the equator and the poles, but it absolutely does not set the rhythm. On Jupiter, the deep, persistent energy comes from below, not from above. It is a world that, quite literally, makes its own internal warmth, its own self-sustaining climate. That warmth, however, does not distribute itself evenly. The constant rising gas creates the pale, high-pressure zones, while the equally constant sinking gas forms the darker, lower-pressure belts. Each band is a ribbon of different temperature and chemistry. Between them, powerful jet streams sweep around the planet, efficiently transporting energy from place to place. The resulting circulation is so vast so stable and so consistent that many of the patterns have persisted for centuries, giving the planet its powerful, reliable appearance. The Great Red Spot, for instance, may owe its incredible longevity directly to this deep, steady internal heat, a constant flow of energy that keeps the atmosphere perpetually churning from the bottom up. Despite the intensity of its storms, Jupiter's climate has a profound long-term consistency. It does not experience seasons like Earth or Mars because its axis is tilted only about 3 degrees relative to its orbit. This means the sunlight it receives changes hardly at all throughout the year. There is no true summer, no winter, and no spring, just a continuous slow rotation under a nearly constant sun. The complete lack of powerful seasonal forcing allows the massive, large-scale atmospheric patterns to persist for decades, even centuries, without major interruption. This consistency, however, does not mean the planet is simple. Beneath the visible, familiar stripes and ovals, Jupiter is full of subtle, enduring rhythms and sudden, dramatic surprises. Every so often, new, immense storms appear from the depths, bright white plumes rising through the darker belt, expanding over weeks into enormous planet-spanning disturbances. These powerful outbursts can temporarily rearrange entire regions of cloud, altering the colors and banding that astronomers have tracked for generations. Jupiter's weather may seem steady, but it breathes in slow periodic cycles, capable of remaining calm for years and then suddenly becoming eruptive, as if the planet occasionally adjusts its atmospheric balance before settling back into its familiar stripes. Lightning is another spectacular expression of this internal energy. Most powerful flashes occur in the humid water cloud layer, far below the upper ammonia haze, where convection is at its strongest. The massive bolts that flash across Jupiter's night side are immense, some hundreds of times more powerful than a typical terrestrial lightning strike. Each one illuminates the surrounding clouds, momentarily revealing the complex structure of the storms within. These flashes are Jupiter's pulse, silent proof that the planet's immense energy is constantly on the move. In a profound way, Jupiter is a world-sized hearth, one that has been slowly burning and settling since the dawn of the solar system. It glows not because of light from the sun, but because of its own enduring warmth, its own gravitational memory.
Every storm, every flash of lightning, and every convective plume is part of that ancient internal fire, quietly expressing itself through gas and cloud.
As we marvel at this restless, powerful balance, we must remember that much of what we know about it comes from the quiet eyes and delicate instruments we have sent there, mechanical extensions of our curiosity, hurled across space to listen to Jupiter's winds, measure its gravity, and trace its invisible, enduring heat. The next chapters in the giant planet's story belong to them, the silent explorers that have watched the king breathe and patiently learned to read its most violent storms. They are the eyes and ears that have traveled millions of kilometers to decode the profound messages held within the planet's spinning depths. For centuries, Jupiter was a magnificent mystery seen only through lenses, a distant orb of stripes and storms gliding silently across the night sky. Then in the mid-20th century, humanity decided it was time to pay the king of planets a visit. One by one, our mechanical messengers set sail across the void, bearing profound questions instead of tribute. They traveled for years, braving cold and intense radiation, to look closely at a world so immense that even sunlight takes nearly an hour to reach it. The very first to arrive were the pioneers, small, robust scouts built purely for discovery. Pioneer 10 flew past Jupiter in 1973, becoming the first spacecraft to successfully cross the asteroid belt and the first to encounter the giant planet up close. Its twin, Pioneer 11, followed the next year. These early explorers were simple by modern standards. Their computers had less memory than a pocket calculator, but their courage was unmatched. As they approached Jupiter, they entered a realm saturated with powerful radiation, strong enough to instantly fry electronics. Their instruments trembled under the onslaught. Yet they endured long enough to send back the first direct measurements of the planet's magnetic field, its radiation belts, and its atmosphere. For the first time, Jupiter was no longer a distant point of light, but a physical, powerful place. The pioneers' findings astonished scientists. They revealed a magnetic field so strong it filled a volume of space larger than the Sun itself, and confirmed that the planet emits far more heat than it receives. Pioneer 11 even took humanity's first blurry, close-up images of the Great Red Spot, glimpsing its swirling complexity from just over 40,000 kilometers away. Those initial grainy photos were the opening lines in Jupiter's modern story. Then came the Voyagers. Launched in 1977, Voyager 1 and Voyager 2 were the great surveyors of the outer solar system, the first grand tourists. When they reached Jupiter in 1979, the view was truly breathtaking. Their cameras revealed the planet in vivid color, showing immense rolling clouds, turbulent belts, and delicate patterns of motion that changed from hour to hour. They captured clear lightning flashes in the night, revealed the auroras near the poles, and tracked the swirling eddies surrounding the Great Red Spot. The images transformed Jupiter from a distant idea into a living, dynamic world. But the real, profound shock came from its moons. The Voyager flybys uncovered actively erupting volcanic plumes on Io, intricate ice fractures on Europa, and the distinct grooved terrains on Ganymede. It was as if a whole miniature solar system had been hidden in plain sight. For the first time, scientists began to see Jupiter not as a single planet, but as a vast ecosystem of worlds, each shaped by its parent's gravity and magnetism. By the time the Voyagers left, bound for Saturn and beyond, humanity's relationship with Jupiter had changed forever. In the years that followed, other visitors paused to admire the giant on their way elsewhere. Cassini, bound for Saturn, flew past in 2000 and took exquisite high-resolution images of Jupiter's cloud tops. The New Horizons spacecraft, heading to Pluto, swung by in 2007 using Jupiter's gravity for a crucial slingshot to accelerate it toward the outer edge of the solar system. Each of these brief encounters added valuable pieces to the puzzle, refining our maps and improving our understanding of the planet's immense energy. But one mission dared to stay. In 1995, the Galileo spacecraft arrived after a 6-year journey and became the first to orbit Jupiter. Named for the man who first spotted its moons through a telescope in 1610, Galileo was a brave, persistent explorer. Despite a technical failure that kept its main antenna from fully opening, forcing engineers to transmit data slowly, like sending postcards through a straw, Galileo accomplished far more than anyone dared hope. It dropped a small probe directly into Jupiter's atmosphere, a crucial 1-hour plunge through layers of cloud and storm before the crushing pressure finally silenced it. That descent gave us our first direct glimpse of Jupiter's weather, the thickness of its clouds, and the surprising dryness of the air in certain regions. Meanwhile, the orbiter studied the planet and its moons for years, revealing details of their magnetic fields, internal structures, and the first strong hints of subsurface oceans. After 14 years in space, Galileo's mission ended in 2003 when it was deliberately guided into Jupiter's atmosphere to prevent it from accidentally contaminating Europa, a potentially habitable world. Then, more than a decade later, a new messenger arrived, one designed specifically to unravel Jupiter's deepest mysteries. Juno, launched in 2011 and arriving in 2016, entered a highly elliptical polar orbit, looping from pole to pole every 53 days. Unlike previous missions that skimmed around the equator, Juno looked down from above, giving us our first views of the poles, regions of swirling, chaotic storms unlike anything seen elsewhere. Its instruments measured tiny changes in the spacecraft's motion, allowing scientists to map the distribution of mass within the planet, giving crucial clues to the structure of its core. Its magnetometer, mapped the planet's magnetic field in exquisite detail, showing that it is far more complex and lopsided than expected. Perhaps the most surprising discovery of the Juno mission was the nature of Jupiter's interior. Juno's data suggested that the planet may not have a distinct solid core at all, but rather a fuzzy core, a vast region where rock, ice, and hydrogen gradually mixed together. Other surprises followed. The discovery that Jupiter's powerful jet streams extend thousands of kilometers below the visible clouds, and the unexpected concentrations of ammonia in some regions, suggesting deep atmospheric currents that move material unevenly. For all their technical brilliance, these spacecraft are at heart extensions of human curiosity. They are machines built by human hands to stand in the punishing radiation and cold where no person ever could, transmitting knowledge bit by bit through the blackness of space. There's something deeply humbling about that. Silent explorers orbiting a planet of storms, patiently translating chaos into understanding. As Juno continues to send back data, its mission reminds us that exploration is never truly finished. Each discovery raises new questions about Jupiter's origins, its structure, and the stories it still holds in its swirling depths. And sometimes, even as we study the giant on our own terms, it reminds us that not every visitor arrives by invitation. Jupiter's immense gravitational reach extends far beyond its shimmering clouds and its majestic moons. And every so often, something unplanned wanders too close to the king, resulting in a dramatic, powerful encounter. For centuries, these events were simply fleeting bright flashes. But in July of 1994, Jupiter became the colossal stage for one of the most significant astronomical events ever witnessed by humanity: the collision of a comet named Shoemaker-Levy 9. The year before, this comet, originally a single body, had been violently torn apart by Jupiter's overwhelming gravity during a close approach. Its fragments, more than 20 distinct pieces, each several kilometers wide, lined up like glowing massive beads and plunged into the planet one after another. For a mesmerizing week, the world watched through telescopes as these icy remnants slammed into the giant, creating colossal fireballs that rose higher than the planet's limb and leaving dark, atmospheric scars larger than the Earth itself. It was a spectacular celestial collision, both terrifying in its scale and beautiful in its destructive clarity, and it served as a vivid, powerful reminder that the solar system is not a quiet place. When those fragments struck, they did not hit a solid surface, as Jupiter has none. Instead, they dove into the planet's deep layers of gas, compressing and heating them until they exploded in bursts of light and energy. Each impact released more energy than millions of nuclear bombs. Telescopes on Earth saw giant plumes of gas and debris rise thousands of kilometers into the atmosphere, followed by massive, dark marks that spread and drifted with the planet's powerful winds. These distinct bruises lingered for months, vast smudges of carbon and dust swirling within the endless flow of Jupiter's clouds. It was as if the planet itself had quietly absorbed the immense blows and carried the temporary memory on its skin. For scientists, those scars were not just dramatically impressive, they were profoundly revealing. By studying the impact sites, astronomers could learn how Jupiter's atmosphere behaves under truly extreme conditions. The plumes expose deep layers of gas that are usually completely hidden from view, offering invaluable insights into temperature, composition, and cloud dynamics. The way the scars evolved and dispersed over time helped scientists refine computer models of how energy moves through the vast atmosphere, how deep winds circulate, and how debris disperses across a rapidly rotating planet. Shoemaker-Levy 9 was, in effect, a massive accidental experiment, one no scientist could have dared to plan, but one that taught us more about Jupiter in a single week than decades of quiet observation. The event also forcefully reminded us of Jupiter's terrifying gravitational might. The same force that captured the comet and tore it apart is the same force that shapes the orbits of countless asteroids and comets across the entire solar system. Jupiter acts like a cosmic gatekeeper, its immense gravity constantly influencing the paths of any object that strays too close to the Sun. Some wanderers are flung outward into distant, harmless orbits, while others are pulled inward, sometimes, ironically, toward Earth. This has led to the popular, comforting idea of Jupiter as the solar system's great protector, a planetary shield that intercepts or deflects dangerous comets before they can threaten the inner worlds. There is much truth to that image. Jupiter certainly captures and absorbs its share of wandering debris. Its huge gravitational cross-section and deep gravity well make it an incredibly effective sink for comets and asteroids. But that same powerful gravitational reach can also act as a slingshot, redirecting some bodies directly toward the inner solar system instead of away from it. In this sense, Jupiter is both guardian and gambler, a planet that sometimes saves, sometimes risks, and always plays by the immutable rules of gravity. The very same force that pulled Shoemaker Levy 9 into destruction could, under different circumstances, send another comet Earth's way. Jupiter doesn't choose sides. It simply balances the celestial books. Since that spectacular week in 1994, astronomers have continued to vigilantly watch Jupiter for similar impacts, and the planet has not disappointed. In 2009, an Australian amateur astronomer spotted a new, dark scar near the South Pole, clear evidence of another large object colliding with the giant. Smaller, brilliant flashes have been detected since then, caught by both professional observatories and dedicated backyard telescopes. These brief, bright bursts, often lasting only a few seconds, are thought to be meteoroids or small asteroids burning up high in the upper atmosphere. Jupiter, it seems, continues to collect the wandering remnants of the solar system, sometimes quietly, sometimes with dramatic, visible flair. Each impact, large or small, teaches us something new. The brightness of the flash reveals the speed and size of the incoming body. The chemical signatures left in the aftermath tell us what the object was made of: ice, rock, or a combination of both. The way the atmosphere responds gives vital clues about its density, its layers, and the depth at which the enormous energy dissipates. In essence, every strike is a natural probe, a violent but invaluable form of exploration. These collisions also help scientists refine our understanding of planetary defense. By studying Jupiter's encounters, we learn how comets fragment under tidal stress, how debris behaves after impact, and how shock waves spread through thick atmospheres. The lessons scale upward and downward alike, from gas giants to terrestrial worlds. What happens on Jupiter can directly inform how we model impacts on Earth, how they release energy, distribute dust, and potentially alter climate. Even in chaos, there is deep education. From another, larger perspective, Jupiter's role as both shield and scatterer has profound long-term consequences for the architecture of the solar system itself. Its gravity has shaped the orbits of countless small bodies, clearing the region between Mars and itself to create the structured asteroid belt and defining the paths of comets in the distant Kuiper belt. Without Jupiter, the inner planets might have faced far more frequent, catastrophic bombardments in their early histories. Earth, for all its life and oceans, may owe some of its stability, and perhaps even its very habitability, to the presence of the self-appointed giant next door. There's something elegantly beautiful about this balance. Jupiter is the solar system's powerful enforcer and silent historian all at once. Every impact mark is a note in the planet's long record of encounters, written in fleeting ink across its clouds. They fade within months or years, erased by the persistent winds. But for a time, they tell the story of an ancient process still profoundly at work: gravity's endless habit of reshaping, redirecting, and reminding. If you were to look at Jupiter now, you'd see no visible trace of those dark marks. The winds have swept them away, and the planet has returned to its usual magnificent tapestry of creams and ochres. Yet somewhere beneath the clouds, the traces still exist in chemical memory. The planet itself remembers, even if our eyes cannot see it. These encounters are not just accidents. They are silent conversations between worlds and wanderers, each impact a punctuation mark in the long, flowing sentence of time. And as we step back from Jupiter's banded surface and its fleeting bruises, a much larger picture comes into view, reminding us that the lessons it offers about gravity, formation and resilience extend far beyond its own orbit. In studying Jupiter, we glimpse not just the heart of our own solar system, but the fundamental nature of giant planets everywhere. As we contemplate Jupiter's profound role within our own solar neighborhood, a larger realization unfolds. Jupiter is not alone. Across the vast expanse of the galaxy, powerful telescopes have uncovered thousands upon thousands of planets that powerfully echo its form. These are the exoplanets, worlds of gas and cloud, immense and mysterious, circling distant alien suns. Some are far larger, some smaller, some searingly hot, and some adrift in the cold. Each one adds a new, unique note to the immense cosmic symphony of worlds, a subtle variation on the magnificent theme that Jupiter first introduced in our own system. Yet in this growing orchestra of planetary giants, our own colossal world remains the fundamental archetype, the first gas giant we ever truly knew, and still the essential key that helps unlock the silent, complex stories of all the others. When astronomers first began discovering exoplanets in the 1990s, they naturally expected to find systems built much like our own, rocky worlds close to their stars, and gas giants orbiting far away in the distant cold. Instead, the universe delivered a dramatic surprise. The first worlds to reveal themselves were the hot Jupiters, enormous gas giants orbiting astonishingly close to their stars, sometimes completing a full orbit in just a few Earth days. These planets, like 51 Pegasi b, utterly defied all existing expectations about how planets should form. They were bloated by intense heat, often tidally locked, so that one side faced eternal, scorching day while the other remained in perpetual night. Their massive atmospheres whipped by supersonic winds and glowing faintly from their own intense warmth. At first, scientists thought these exotic worlds might be rare oddities, but as more discoveries rapidly followed, it became clear they were common. Their existence violently challenged every assumption about how planets form and where they reside in a solar system. Our Jupiter orbits far from the Sun in a region cool enough for ice to condense, the crucial frost line. There, solid grains of ice and rock accumulated into a massive core that could capture vast amounts of gas. Close to a star, such volatile materials would have evaporated before they could form anything substantial. So how could hot Jupiters exist so close to their suns? The profound answer, it seemed, was internal and external motion. The leading theory is that many of these giants didn't form where we observe them now. They were born farther out, much like our own Jupiter, and later migrated inward through complex interactions with the surrounding disk of gas and dust, or through violent gravitational encounters with other massive planets. This migration drastically reshaped their systems, often pushing smaller, rocky worlds aside or swallowing them altogether. Some hot Jupiters may have even plunged directly into their stars after spiraling too close. It is a violent form of celestial choreography, one that shows just how turbulent and dynamic young planetary systems can be. But not all exoplanetary giants ended up so near their suns. Between the extremes of hot Jupiters and cold, distant giants lie the warm Jupiters and many Neptune-sized worlds, planets that bridge the gap between pure gas and rock,
often with thick, layered atmospheres and complex systems of clouds.
Their immense diversity tells us that planetary formation is not a single, rigid process, but a vast spectrum of outcomes. A small change in initial conditions, A little more gas here, a little less dust there, can lead to wildly different results. By meticulously comparing these distant alien worlds to our own Jupiter, scientists can test how universal its story might be. Did all giant planets begin with a solid core that grew massive enough to attract gas? Or did some form rapidly, collapsing directly from the disk material in a kind of miniature star formation event? Jupiter itself may hold the answer. Its fuzzy core, as revealed by Juno, is a clue that both processes could have played a subtle, combined role. The patterns we see elsewhere suggest that Jupiter's birth was not a one-off miracle, but one highly successful version of a common cosmic theme. Jupiter also provides the fundamental context for understanding habitability. Its immense gravity and early history, specifically its relatively mild migration, likely shaped the stable distribution of material in our solar system. By helping to hold the outer region stable and scattering dangerous debris, it may have helped Earth remain safe enough for life to flourish. In other systems, the presence or absence of Jupiter-like planets can be the ultimate deciding factor in whether smaller, Earth-like worlds survive or perish. Too much migration, and the inner regions become gravitational chaos. Too little, and the system may never form rocky planets at all. In that profound sense, Jupiter is not just a planet. It is a sculptor of worlds. Its influence extends beyond its own orbit, quietly defining the potential for life across the entire solar system. Even today, as astronomers map thousands of distant systems, they find clear echoes of this fundamental relationship. Some stars host giants far from the habitable zone. Others have chains of smaller gas planets locked in precise resonances that strongly recall Jupiter's gravitational dance with its own moons. There are systems with multiple giants in highly eccentric orbits, where each world's gravity keeps the others perpetually on edge, and systems with none at all, where rocky planets reign undisturbed. In every single case, the gas giants are the architects, setting the gravitational tone for everything around them. The variety is astonishing. Some exoplanetary Jupiters are so close to their stars that their atmospheres are being boiled off into space, forming glowing, trailing tails of gas like comets. Others orbit far out in the perpetual dark, with temperatures hundreds of degrees below freezing. A few wander between stars entirely, cast adrift by past gravitational encounters, roaming the galaxy as planetary nomads. Each one offers a different, fascinating answer to the question of what it truly means to be a giant planet. And yet, amidst all this spectacular diversity, Jupiter's familiar presence feels strangely central. It remains the essential reference point against which all others are measured. Its structure, its powerful storms, its immense magnetic field, and its surprising collection of moons, these have become the universal yardstick for understanding gas giants everywhere. When astronomers detect faint light curves from a distant world, they often describe its winds, clouds, or chemistry in Jupiter units. It has become not just a planet, but the gold standard of comparison, the original
resonant note from which all the harmonies of giant worlds are tuned. The more we learn,
the more we see that Jupiter's story is both universal and profoundly unique. It faithfully follows the rules of planetary physics, but plays them with its own careful, stable rhythm. Its relatively mild migration may have been the very key that preserved the stability of the inner solar system, a delicate balance that allowed Earth to remain calm while chaos reigned elsewhere. Many systems, by contrast, appear to have sacrificed their inner worlds when their own massive giants wandered inward. Jupiter's restraint, in a sense, is the very reason we can look out at the stars and study other Jupiters at all. There's a quiet, beautiful poetry in that. The idea that our planet's colossal protector might also be our silent interpreter, teaching us how the universe builds and rebuilds itself. Every exoplanet discovery, from the blazing hot Jupiters to the frozen giants beyond their star's light, adds another complex verse to that same cosmic song. The melody is familiar, but the tempo changes with every system, each variation playing on a theme that began right here. circling in the dark beyond Mars. If the galaxy were a vast, intricate symphony, Jupiter's note would be deep and powerfully resonant, a fundamental tone from which other worlds take their pitch. We can now hear that familiar chord echoing everywhere. And as we listen to those distant cosmic echoes, we find ourselves nearing the calm at the edge of understanding, a place where knowledge fades gently into profound wonder, and where Jupiter, the king of planets, continues to quietly whisper the music of creation. We have completed our long, quiet journey around the king of planets, drifting through its history, its immense invisible fields, and the delicate dance of its worlds. Now in the final calm, we gather the themes of Jupiter's being. In the great gallery of the solar system, Jupiter stands as both a masterpiece and an ongoing mystery, a world where chaos and order are not enemies, but enduring dance partners. Everything about it is a magnificent act of profound balance. Storms that rage for centuries, yet remain perfectly contained. Winds that sweep ferociously, but create rigid, beautiful structure. A planet born from explosive disorder that now holds the entire system in harmony through relentless motion. To understand Jupiter is to see precisely how the universe sculpts beauty from turbulence, not by erasing the chaos, but by patiently shaping it into an eternal rhythm. From the earliest, fine dust of the protoplanetary disk, Jupiter rose first. Its immense gravitational birth shaped everything that followed, sweeping the early solar system clean, rearranging orbits, protecting smaller worlds, and defining the structure of the cosmic neighborhood. Out of the chaos of gas and rock, it gathered itself, capturing enough material to become a world so massive that it still glows with leftover heat from its creation. That same original heat keeps its atmosphere perpetually alive today, feeding powerful convection and circulation that have endured for centuries. In the quiet immensity of its gravity, it became the conductor of the solar system's orchestra, setting the stable pace for planets, asteroids, and wandering comets alike. Its complex colors, creams, golds, rusts, and ochres are the visible, beautiful trace of chemistry and sunlight working together. Ammonia, sulfur, and water, along with trace elements, mix and swirl in layered clouds, their hues shifting subtly with altitude, temperature, and time. Those persistent stripes that stretch around the planet are not decoration. They are the visible product of jet streams flowing in alternating directions, the necessary result of rotation so incredibly rapid that the Jovian day lasts less than 10 hours. From those bands rise immense storms, some new and bright, others ancient and enduring. The great red spot, vast enough to swallow Earth, has spun for centuries, gently fading and reshaping, yet never losing its commanding presence, a persistent eye of order in a sea of turbulence. Beneath the swirling, stormy surface, the planet deepens into profound mystery. Hydrogen, the lightest element, is pressed under unimaginable weight until it behaves like a dense, liquid metal, constantly conducting electricity and generating a magnetic field so powerful it stretches millions of kilometers into space. That invisible magnetosphere traps charged particles, silently sparks the beautiful auroras at the poles, and hums with magnetic energy, a colossal song resonating through the void. It is one of the strongest fields in the solar system, a constant reminder that even unseen forces can dramatically shape the fates of entire worlds. And orbiting precisely within that powerful field is a magnificent miniature system of its own.
Dozens of moons, each with its own compelling story. Io relentlessly volcanic, forever reshaped by Jupiter's tidal pull.
Europa, the quiet ocean world, hiding vast, warm, saltwater seas beneath its frozen crust. Ganymede, the magnetic moon with an ancient iron heart that subtly echoes its parent's dynamo. And Callisto, the archivist of ancient impacts, a frozen time capsule of the solar system's earliest days. Together, they make Jupiter not just a planet, but a self-contained ecosystem, a cosmic family bound by gravity and precise rhythm. Even the way those moons move speaks to order rising from deep chaos. Their orbits are locked in Laplace resonance, perpetually tugging at one another in a steady gravitational dance that keeps their interiors warm and geologically active. Every subtle pull, every stretch, every minute oscillation transfers energy through their crusts and cores. It is a quiet, continuous conversation, measured in tides and time, a gravitational heartbeat that has pulsed for billions of years. Through the quiet eyes of our spacecraft, the pioneers, the Voyagers, Galileo and Juno, we've learned to patiently listen to that heartbeat. They have shown us that Jupiter is not static, not simple, and not uniform. It is deeply layered, immensely dynamic, and still filled with surprises. The vast, fuzzy core blurring the line between rock and gas, the jet streams anchored thousands of kilometers deep, all tell us that even the mightiest of worlds remains an ongoing work in progress. And sometimes the universe itself sends its own messages, as with the fragments of Comet Shoemaker-Levy 9, which fell one by one into Jupiter's atmosphere. Those dark, fading marks reminded us of how gravity binds and breaks, how creation and destruction share the same fundamental physics. They also revealed Jupiter's double role, protector and provocateur, shield and scatterer. The same gravity that swallows comets also flings them across the cosmos, a force of perfect, neutral balance rather than personal preference. Beyond our solar system, Jupiter's reflection appears again and again, in hot Jupiters circling close to alien suns, in cold giants orbiting far in the dark, and in warm, misty worlds that lie between. Each is a spectacular variation on the same recurring theme: gravity gathering, heat stirring, and order emerging. The story of Jupiter, written in hydrogen and helium, repeats itself across the galaxy in 1,000 different ways. It is the fundamental, enduring pattern that connects us to distant stars, a universal design of motion, magnetism, and cosmic patience, and perhaps that is Jupiter's greatest, most profound gift: perspective. It teaches us that complexity and deep calm can coexist. In its endless winds, we see the same processes that formed galaxies and atoms alike: energy seeking balance, and chaos slowly settling into rhythm. The planet is not a symbol of dominion or violence, but of immense, quiet endurance, of a system that finds harmony not by resisting disorder, but by perfectly weaving it into something magnificent. For all its grandeur, Jupiter rules gently. It does not command through conquest or destruction, but through balance. It is the only king in the solar system whose crown is made of faint dust and whose power comes from continuous, invisible motion. In its endless motion, we find a great lesson: the knowledge that beauty is not the absence of chaos, but its transformation. That even in the most violent systems, elegant patterns will always emerge. That the universe does not rush toward fleeting perfection, but toward lasting balance. When chaos becomes order, it becomes a world. And for a while, it becomes a profound, comforting home for the eyes and the mind. Thank you for drifting through this quiet journey tonight. May Jupiter's vast, enduring calm follow you into rest. May your thoughts, like the planet's magnificent clouds, find their gentle, quiet rhythm as you drift towards sleep. The stars will keep watch, the storms will keep spinning, and all will remain in motion. Softly, endlessly, beautifully,